Is there a giant mega-sun in the center of our Milky Way? Scientists actually thought so for a while because it's the brightest place in the galaxy. It has millions of stars packed into a small area. This area is called the gigantic bulge. The gigantic bulge has millions more stars per light year than any other part of the galaxy. It can be 10 million times denser than our part of the neighborhood. In some cases, stars in this region are only 5 light days apart. That's like if there was another star in our solar system a bit further away than Pluto on a space scale. But why is this place so dense? When galaxies form, a lot of gas and dust come together under the force of gravity. This material gathers up and eventually forms stars. Gravity and angular momentum balance out, and it starts looking like a flat disk with a pretty bright, bulging, dense core. The stars live their comfy lives, and once they get to the finishing line, they collapse under their own huge weight. Then, the black hole forms. Black holes love to eat everything around them, and the more they eat, the bigger they get. And what place is more perfect for a fine dinner than the galaxy center, where all the space stuff is packed together? So it starts eating surrounding gas and dust, forming an accretion disk. As this material spirals into the black hole, it heats up and emits a lot of energy, which makes the center of the galaxy even brighter. That's why you can find both supermassive black holes and galactic bulges in the centers of all galaxies. The galactic bulge at the center of the Milky Way looks a bit like an ellipse. That's a classical bulge. Stars aren't like our sun. They move randomly in all possible directions and planes. Plus, they all move at different speeds. So gravity is going crazy there, and this makes the bulge look more like a sphere, or an ellipse. Since they were the first ones to form, they have some of the most ancient stars in our galaxy. But there are also some places of star formations and lots of younger, massive stars that are less than 100 million years old. As we move farther away from the center, things get a bit calmer. Stars start rotating uniformly and become stable. Right now, Earth is in one of the Milky Way's spiral arms called the Orion Arm, pretty far away from the galactic bulge. In our part of the neighborhood, stars are usually about 4 or 5 light years apart. This means that most of a galaxy is actually just black, empty space. Our black hole is called Sagittarius A star. It's a monster about 4 million times the mass of our Sun. It's also about 32 million miles in size, almost like the distance between Mercury and the Sun. But don't worry, it's not attracting the Milky Way inside it, and it's not gonna eat us. These black holes are actually super small compared to the entire galaxy, so they can only eat whatever's around. Right now, many stars orbit Sagittarius A star. And even though it emits a huge amount of energy, we can't see its light from Earth without a lot of scientific effort. But why don't we see the center itself? The galactic bulge is so bright that even though it's 26,000 light years away, we should see it shining brightly in our sky. Yet we don't. Turns out it's all because of space dust. There's a lot of dust between us and the core, and it absorbs most of the visible light. We can only look at the galactic core using other types of light, like near-infrared, gamma ray, and so on. NASA has images of the core in different types of light, and it shows how scarily bright the center is without the dust blocking our view. But not all bright regions are blocked by gas and dust. For example, when we look at dense clusters like the Messier 13, the stars are so close together that they look just like a white spot. Most of our telescopes can't separate them from each other. The satellite galaxy M32, our neighbor near the Andromeda galaxy, has about 84 stars per light year. It's so dense that stars can't be resolved even by the Hubble Space Telescope. To get the idea, our solar system is 2 light years long. We'd see about 168 stars outside our window if we were there. Our closest star is Alpha Centauri. It's about 4 light years away from the Sun. If it was just a couple of light days away, it would shine much brighter than the full moon. So if we somehow managed to survive in crazily dense star regions, the sky would be white all day long. But it's unlikely that we'd make it. As we get closer to the center of the Milky Way, the chances of finding life get super slim. The gravity of stars is going wild with chaotic movements, so there are barely any planets around. On those miracle planets, the radiation from cosmic rays is skyrocketing. Supernova blasts and star collisions nearby become an everyday occasion, and all the gas around makes it basically impossible to breathe or even see properly. At the same time, as we move further away, there are fewer stars around. Elements that are super useful for life, like carbon, oxygen, and iron, are produced by stars, so they also drop. Too much radiation is awful, but too low radiation means that there's not enough energy to support chemical reactions, like photosynthesis. Which is why, if there is extraterrestrial life, it would most likely be somewhere in the middle of different galaxies. But some galaxies get their brightness from a so-called active galactic nucleus. These are extremely energetic regions at the center of some galaxies. They shine much brighter than any stars imaginable, although it mostly shines only in certain parts of the electromagnetic spectrum. The brightness comes not from the stars, but from the accretion disk around their supermassive black holes. As the material slowly falls into a black hole, it gathers around it and creates this flat, spinning disk of gas, dust, and other stuff. Since the gravity and friction there are insane, this disk heats up and starts emitting enormous amounts of energy. Also, this disk spins incredibly fast, almost at the speed of light. Because of that, collisions there happen all the time, and they're unimaginably powerful. They release even bigger amounts of energy. Most galaxies don't have an AGN. Those that do, like the galaxy M87 in the Virgo constellation, are called active galaxies. There are also different types of AGNs: the Seyfert galaxies, radio galaxies, and finally, the winners of our space brightness competition, quasars. Imagine things so bright that they can outshine the entire galaxy they belong to. Quasars are a specific type of active galactic nucleus, the most extreme and luminous form. They belong to the supermassive black holes, the biggest ones in our universe. Quasars are like a combination of several things. First, they're the brightest accretion disks in our world, because of their behemoth black holes eating everything around. But they have some cool features. For example, they have powerful jets of particles that shoot out from the poles of the black hole at nearly the speed of light. These jets add up to the brightness of the quasar, although they can only be seen in radio wavelengths. The energy they emit is so intense that they can be seen billions of light years away. However, the nearest quasar to us is 600 million light years away, so we can't see them with backyard telescopes. So, when we look at a galaxy through a telescope, we usually see only the brighter core, not the outer parts. Unfortunately, our eyes just aren't made to see things like the active galactic nucleus. So, these stars are the brightest things we can see. But what a beautiful sight it is.
Hold on to your telescope, space rat. Scientists have made an astonishing discovery. They've found the ancient heart of the Milky Way galaxy. But what is this ancient heart? And what does it tell us about the history of our galaxy? Let's find out. Is that it? Yes, and thank you, Captain Jack. My pleasure. What can I say? He's a space pirate. Now, the Milky Way isn't just a candy bar, but a majestic spiral galaxy that's home to billions of stars, planets, and other celestial objects. And it's all spread out over a distance of about 100,000 light-years. The Milky Way has a distinct shape, with a central bulge and spiral arms that extend out from it, kind of like what I look like from the side. The spiral arms are like the suburbs, where the stars are more spread out and the neighborhoods are quieter. They're made up of gas, dust, and stars that all move together in a circular pattern around the center. In between the spiral arms, there are vast regions of empty space, known as interstellar space. Here you can find wispy clouds of gas and dust, as well as some of the most spectacular sights in the galaxy, like massive star-forming regions and colorful nebulas. The Milky Way is also surrounded by a huge halo of dark matter, a mysterious substance that we can't see but can feel its gravitational effects on the galaxy. This halo helps to hold the galaxy together, and it extends out much farther than the visible parts of the Milky Way. And finally, here's the center. Here, the most action happens. In the center of the Milky Way, there's a supermassive black hole, which is about 4 million times more massive than our Sun, Sagittarius A star. This black hole is responsible for some of the most energetic events in the galaxy, like the emission of powerful jets of energy. Remember the famous first photo of a black hole that flew across the internet? It was Sagittarius A star. We managed to capture this black hole because it's the closest one to us. All in all, the center of the Milky Way is full of stars that are tightly packed together, forming a dense cluster. And it was here that astronomers recently made a new epic discovery. The heart of our Milky Way galaxy has been found, and boy oh boy, is it an old-timer. Hey, who are you calling an old-timer? Now, a team of brilliant scientists have found a cluster of 18,000 stars, born right after the Big Bang. Together, they form the ancient nucleus of our Milky Way. These stars date back to a time when our galaxy was just a wee little baby, a mere collection of proto-galaxies, huddling together to form a bigger and better thing. The scientists called it the poor old heart of our Milky Way. Can you believe it? These ancient stars are over 12.5 billion years old. And yeah, maybe they account for a mere 0.2% of our galaxy's total mass. But that doesn't matter. These stars are the building blocks that form the core around which all the other stars and planets took shape. But how exactly did they become this heart of the galaxy? How did they form? And how did we discover all that? To answer these questions, we'll have to plunge into the past, a very, very distant past. Once upon a time, about 14 billion years ago, there was the Big Bang. Our universe was born. At first, it was incredibly hot, but as time passed, things started to cool down and tiny pockets of gas began to clump together due to the force of gravity. These were the first galaxies. The Milky Way is one of these galaxies. It also started as a small clump of gas and dust, but over time, it began to take shape. The very first stars, protostars, began to form within the clouds, and their gravitational pull caused more stuff to come together. This process continued for millions of years until the Milky Way was formed. But to learn the history of our galaxy in more detail, we need to find these protostars, and this is far from an easy task. Researchers have discovered the ancient heart using a neural network to analyze data from the European Space Agency's Gaia mission. The Gaia telescope is a space observatory launched by the European Space Agency in 2013. Its job is to map the position and movement of more than 1 billion stars in the Milky Way galaxy. 1 billion stars! That's like counting every grain of sand on a beach. It's a huge job, but Gaia is up to the task. So, how did they do it? The telescope has 2 cameras that take pictures of the sky at the same time. These cameras are so powerful that they can detect stars that are 1 million times fainter than those visible to the naked eye. Gaia takes many pictures of each star, and this allows us to track their movements with incredible precision. Thanks to the data collected by Gaia, astronomers are learning more about the structure and history of the Milky Way. They've discovered new details about the stars, including their ages, temperatures, and chemical compositions. Gaia is also helping astronomers search for exoplanets, or planets that orbit stars outside of our solar system. So, for this research, astronomers used Gaia and the most accurate 3D map of the Milky Way ever compiled. They had to analyze around 2 million stars to find the primordial group. One way that astronomers can determine the age of stars is by looking at its brightness and temperature. This way, they study a brief phase of stellar evolution known as subgiants. But imagine searching through the huge center of the Milky Way for the tiniest group of stars that are older than 12.5 billion years. This is like searching for a needle in a haystack. Luckily, they had a trump card up their sleeve: metals. You see, in the early universe, the cores of these stars were so hot and dense that they were able to smash atoms together to form heavier elements. These heavier elements are called metals in astronomy, even though they're not really metals like the ones we're used to. The more massive the star, the more metals it can create during its lifetime. When the life of the first stars came to an end, they made a big boom and scattered these metals all around. Metals mixed with other gases and joined the newborn stars, and so on. As time passed and the universe got older, more and more generations of stars formed, each one richer in metals than the last. Can you guess what that means? The older the stars, the less metals they should have. So now it was time for some galactic archaeology. The team taught the AI to find the metal-poorest, most ancient stars, and it succeeded. It found a huge cluster, and all of them were within 30,000 light-years from the center of the Milky Way. Then they separated out the stars that formed the ancient heart from the stars that originated in a dwarf galaxy. And finally, we were left with the original stars around which the Milky Way grew. This discovery is incredible. It reveals the remnants of the Milky Way's earliest history. It turns out that simulations of the Milky Way's formation were spot on. The old stars existed just where they were predicted to be. Just imagine, the stars that remember our universe as a baby are still hanging out in the center of our galaxy. Isn't that mind-boggling? So why is this such a big deal? Well, by studying these ancient stars, scientists have discovered some incredible things. For example, they've confirmed that the Milky Way's core began its life stationary and only picked up rotational speed as it grew. In other words, the Milky Way formed from the merging of 3 or 4 protogalaxies, and these stars were its initial core. But even after billions of years and multiple mergers, the heart of the Milky Way has remained intact, like a sheltered oasis in the midst of cosmic chaos. All in all, the Milky Way is a vast and complex place, full of mysteries and wonders waiting to be discovered. It's a true marvel of the universe, and we're lucky to call it our home. But the research isn't over yet. Scientists are eager to learn even more about the formation of the Milky Way and hope to study these ancient stars in even greater detail. Who knows what secrets they might uncover? Maybe they'll even discover what types of supernovas exploded to create the elements we see today.
So, get ready, Space Rat. The adventure is just beginning. Arr!
Oh, fasten your seatbelts. We're setting course for the most bizarre places in our universe, and you'll see the most mysterious phenomena few people have ever seen before. Recently, astronomers have discovered that the supermassive black hole at the center of our home Milky Way galaxy might be leaking. Why is it a significant change? Because it might mean that this black hole, called Sagittarius A star, whose mass is 4.1 million times the mass of our Sun, isn't a sleeping giant as previously thought. It might still be active. And the leakage, recorded by scientists, may be the hole hiccuping while swallowing clouds of gas. Hey, I've been known to do that from time to time. During the research, the team of astronomers used the Hubble Space Telescope. It helped them spot a jet that looked like a blowtorch. It was pushing into clouds of hydrogen at the center of our galaxy. The jet seemed to spew gas like a hose directed into a pile of sand. This often occurs around other active black holes surrounded by the material drawn to them by their immense gravitational pull. Some of this material gets pulled into the black hole, but a small part of it gets swept outward by powerful magnetic fields. The research suggests that when a giant gas cloud gets too close to our supermassive black hole, it gets swallowed, and then the hole belches small jets of matter. Fermi bubbles might be the result of the belches that occurred around 2 to 4 million years ago. But recently, scientists have found another giant glowing bubble of hot gas. It aligned with the jet stretching for 35 light-years or more from the supermassive black hole. Astronomers suspect that the jet could have plowed into this bubble of gas and inflated it. Now, let's visit some other breathtaking places in our universe. But be careful, some of them are extremely dangerous. Like this rotating neutron star called the Black Widow pulsar. Just like its spider namesake, it's munching on its partner, a lightweight brown dwarf star. The more material this pulsar consumes, the more slowly it spins. The energy the neutron star is losing in the process causes the companion star to dwindle. If it does exist, nuclear pasta is the strongest material in the entire universe. Formed from the leftovers of extinguished stars, this substance gets squeezed into spaghetti-like tangles of material. It can break, but only if you apply 10 billion times the pressure needed to shatter steel. How about visiting a planet where it rains glass? Nah, I'd rather not. You see, this bright blue exoplanet looks peaceful and slightly familiar. Don't you think it slightly resembles Earth? But this pretty appearance hides the planet's terrifying nature. The winds blow at 5,400 miles per hour on its surface. That's 7 times the speed of sound. But that's not the worst. It rains glass sideways in this scorching hot alien world. Solar tsunamis are a solar phenomenon dubbed Terminator events. These tsunamis take place at the sun's equator. Disastrous magnetic field collisions seem to cause ginormous twin tsunamis of plasma. These tsunamis tear across the star's surface, moving at a speed of 1,000 feet per second. They can last for weeks at a time and happen every decade or so. Now look at this space body. Its nickname is Electric Hyperion. This Saturn's moon is one of the most bizarre-looking moons in the solar system, but its appearance isn't the strangest thing about it. This pumice stone-like rock, pockmarked with countless craters, is also charged with static electricity, and it's flowing out into space. Look at this, a rogue planet with auroras. Lost in space and drifting through galaxies, rogue planets were once flung away from their parent stars. But one of them, 200 light-years away from Earth, is different from the rest. It's a planet-sized object with a magnetic field 200 times stronger than that of Jupiter. This field is so powerful that it generates flashing auroras in the planet's atmosphere. Be sure to stay away from black holes. Do I really need to warn you? Yep, they're some of the most perilous objects in the universe. But how about mini black holes? Unlike their massive siblings, hypothetical mini black holes could be really tiny, not bigger than an atom. Even so, just one minuscule thing would have the mass of 1,000 sedans. One theory claims that tons of micro black holes could have been created right after the Big Bang and the beginning of the universe. Some scientists even go as far as to say that a couple of mini black holes pass through our planet every day. Ooh, I'll bet you like our next stop, a burning ice planet. Faraway Neptune-sized exoplanet Gliese 436b is a paradox. It's made of scorching hot ice. The planet completes one full orbit around the red dwarf Gliese 436 in just 2 days. It means it's traveling remarkably close to its parent star. That might be the reason the planet's temperatures rarely drop below 800 degrees Fahrenheit. But the strangest thing? The planet hosts huge volumes of water ice known as Ice X, which remains solid despite blistering temperatures. Now, if you love jewelry, this next world is for you, a diamond planet. About 4,000 light-years away from Earth, there's a planet that seems to be one enormous diamond. The planet is denser than any other discovered so far and consists mostly of carbon. It's so dense that astronomers think this carbon might be crystalline. This in turn might mean that at least some part of the planet is diamond. Moons orbiting other moons might exist, or they might not. Astronomers haven't agreed on this one yet. Planets orbit stars, and moons orbit planets. But then, why can't there be moons, also known as submoons, moonettes, and moons? It actually sounds like one of those flowery Hawaiian dresses, moo-moos. But alas, no. Researchers claim that moons could exist, but the host moon has to be massive enough, the moon small enough, and there must be a wide gulf between these moons and the host planet. Now, I'll take you to the living fossil galaxy. DG-SAT-1 is as big as the Milky Way, but it's nearly invisible because its stars are spread out incredibly thinly. But what makes the galaxy unique is that it's sitting all alone, unlike other galaxies of this kind. Those are usually found in clusters. It can mean that DG-SAT-1 was formed in a different era, probably a mere 1 billion years after the Big Bang. If it's true, this galaxy is a real living fossil. Now, you won't be able to see the next space phenomenon, all because people can't see infrared light. And the phenomenon I'm talking about is an infrared stream from space. Ooh. Neutron stars are ultra-dense collapsed cores of giant stars. They usually emit X-rays or radio waves. But in 2018, astronomers discovered a weird stream of infrared light. It seemed to be coming from a neutron star 800 light-years away from our planet. This signal was probably generated by a disk of dust surrounding the star, but this theory hasn't been proven yet. Behind the orbit of Neptune lies the mysterious Kuiper Belt, filled with massive icy objects. The most curious thing about this space formation, though, is that scientists fail to explain the pattern of its movement. The only explanation they have is that Neptune might be hiding from our sight a ginormous planet. This hypothetical planet has already got the name Planet 9, and all we have to do is wait until its existence is confirmed, or not. Let's visit our star, but we need to be careful not to come too close, because the Sun's atmosphere is hotter than the surface of the star. While on the surface, the temperature reaches 10,000 degrees Fahrenheit, the upper atmosphere heats up to millions of degrees. Scientists suspect that explosive bursts of heat from the Sun may have something to do with this unique phenomenon. Now, this space object is also worth visiting. Haumea, a dwarf planet orbiting in the Kuiper Belt, has a bizarre elongated shape and 2 moons. The day on this planet lasts 4 hours, making it the fastest spinning big object in our solar system. But the most mysterious thing about Haumea is that the planet has a thin 40-mile-wide ring circling it. Ring-a-ding-ding.
Black holes are massive, the densest objects in the universe. They have such a great mass that their gravitational pull doesn't let anything, even light, escape their clutches. But in this terrifying world of black holes, there are monsters that are in a league of their own. Recently, astronomers discovered a black hole that is 33 billion times as heavy as our Sun. This space giant sits at the center of a supergiant elliptical galaxy called Abell 1201, which is located 2.7 billion light-years away from our planet. This black hole is so large it was given a rare designation, an ultra-massive black hole. No wonder. It's more than 8,000 times heavier than the supermassive black hole at the center of our home Milky Way galaxy. This ultramassive black hole was the first one to be discovered with the help of gravitational lensing. This method is based on the fact that very massive objects such as galaxies bend the light from a more distant object, magnifying it. A great thing about this method of research is that it allows astronomers to study inactive black holes too. It could help us detect loads of new black holes beyond our universe. That's what the area surrounding our galaxy is called. Probably it would help us find some exotic objects we've never seen before. Now, let's speak about another awesome instrument that efficiently helps us explore space, the James Webb Space Telescope. When it stares at young galaxies, which would look like mere red specks to you, it sees an astonishing number of cyclones churning at their centers. Those are black holes. Interestingly, giant black holes were believed to be big players in early cosmic history. But James Webb regularly finds an unexpected number of these beasts. For example, using the telescope, astronomers have detected a supermassive black hole from when our universe was less than 600 million years old. In universe terms, it's just a baby. This is the most distant actively feeding supermassive black hole ever observed. It's located at the heart of its host galaxy called Sears 1019. The black hole is surprisingly small and not massive at all. It's actually one of the smallest found in the early universe. It's equal to approximately 9 million suns. It might sound like a lot, but in reality, supermassive black holes tend to grow to billions of times the mass of our star. There's another unusual thing about this find, and scientists are having a hard time trying to explain it. You see, it's supposed to take way longer than 600 million years for a supermassive black hole to grow to its full potential. The development happens when a black hole either feasts on surrounding matter or merges with a larger black hole. Even black holes similar to the one at the center of our Milky Way galaxy, which is almost 4.3 million times the mass of our Sun, are supposed to be seen in the more recent universe. Actually, scientists have long suspected that supermassive black holes probably existed in the early universe. But this theory has been proven only thanks to the JWST and its infrared eye. It's shown that the black hole Sears 1019 is actively munching on all the matter it can lay its hands on. Such feeding black holes are usually surrounded by swirls of gas and dust, falling inside them, called accretion disks. The gravitational force of a black hole heats this matter, and it makes the disk shine. And that's not all. Extra strong magnetic fields produced in this process channel the matter to the poles of the black hole. From time to time, this matter is released into space in twin, powerful jets. They move at a speed that is close to the speed of light, which generates incredibly bright light. Astronomers were watching the galaxy hosting the unusual old black hole as part of the Cosmic Evolution Early Release Since survey. They saw the galaxy as it was when our 13.8 billion-year-old universe was just 570 million years old. Besides the super old black hole, scientists spotted two other ones. Those probably appeared 1 and 1.1 billion years after the Big Bang. They also discovered 11 ancient galaxies that existed between 470 and 675 million years after the beginning of cosmic history. Now, how about having a look at the biggest black holes astronomers have found so far and finding out what would happen to Earth if one of them was to enter the solar system? NGC 6166 is a monster that has grown to have a mass of 30 billion solar masses. It's an elliptical galaxy that has an active nucleus at the center. It's also one of the most luminous sources of X-rays. The galaxy's supermassive black hole powers two symmetric radio jets in the opposite direction, which is the result of the infall of gas into its center. Another peculiar thing about NGC 6166 is that it shows a blue shift, which means it's moving towards us. Is it time to pack up and move out of our solar system? The next supermassive black hole is located in the constellation of Draco, approximately 10.4 gigalight-years from us. The mass of this supergiant is more than 30 billion solar masses. Besides being incredibly massive, the black hole is also really big. If it replaced our Sun, the diameter of this hole would extend to the orbit of Pluto. The next black hole is one of the most interesting on our list. It has a mass of 40 billion solar masses and is actually a blazar. It's the most energetic of all quasars, super bright distant objects. The blazar's luminosity is 300 trillion times that of the Sun, and more than 25,000 times as great as the luminosity of all 100 to 400 billion stars of the Milky Way galaxy combined. But since the distance to this quasar is about 12.1 billion light-years, we can't see it directly. But we know that the central black hole of the quasar consumes huge amounts of matter, about 4,000 solar masses of material every year. IC 1101 is a supergiant elliptical galaxy. It's the most massive known galaxy so far. Since this galaxy is elliptical, it isn't filled with gas. That's why the star formation in that region is very low. As for the black hole at the center of this galaxy, it lies in the mass range of 40 to 100 billion solar masses and emits clear radio signals. But wait for this champion. Astronomers have discovered a gravitational space wonder that has grown to really unimaginable proportions. The black hole I'm talking about is TON 618, and it's a mind-boggling 66 billion solar masses. Yep, we've got another ultra-massive black hole here. Imagine gathering all the stars in our home Milky Way galaxy and squishing the matter they're made of into one black hole. And it still won't be enough to create a ton 618. If this monster of a black hole replaced the Sun, its radius would be more than 40 times the size of Neptune's orbit. You know that black holes are incredibly dense, but it doesn't mean they're some kind of space predators roaming galaxies and munching on everything they come across. Ton 618, for example, still has a whole galaxy filled with stars and other stuff happily orbiting it without getting pulled inside. So the perception of black holes as giant vacuum cleaners is wrong. In reality, it's incredibly hard to grow a black hole. Try and you'll see. And now, what if a supermassive black hole, like the one that dwells at the center of our home Milky Way galaxy, moved a bit closer to our solar system? The answer is simple. We'd be doomed. The distance between this huge thing and Earth would be several dozens of light years, and still, it would wreak total havoc on our planet. Earth, along with other objects making up the solar system, would be tugged into the black hole's orbit and doomed to spin around it for eternity. But you can relax and breathe out. Such massive black holes stay away from us at the moment.
Okay, here's the deal. Something is bound to happen that can affect everything we've ever known about space and time. You've heard about black holes, right? That denser-than-life type of phenomenon that usually exists in the center of galaxies? Two of them, located 9 billion light-years away from Earth, are expected to collapse into each other. And my oh my, I do not want to be around to see that. Let's get one thing straight. Black holes are the most powerful things in the entire universe that we know of. If they decided to go all Revenge of the Sith on us, we'd be doomed. A black hole was once a massive star that went supernova, meaning that the star collapsed onto itself, and the sheer magnitude of the explosion created a black hole in its place. Oh, by the way, black holes do not pull things inside like a vacuum cleaner. That's just a popular myth. Say we were to replace our Sun with a black hole at the center of the solar system. Not much would change, except that maybe we'd all freeze. Yep. But black holes can do something much worse than vacuum stuff. They can delete the universe itself. If a black hole was to follow a normal timeline, it would go from its creation to total disappearance. But this process is very, very slow. I'm talking about billions and billions of years before a black hole loses its mass entirely. That happens because they're constantly losing their mass every single second. Black holes radiate their mass away, like a boiling teapot loses its water as steam. Yet, things rarely go as planned, both in our lives and apparently in the universe itself. So it wouldn't be that much of a surprise to find out that two black holes are en route to collapse. That's what scientists have found out recently. And let's just say that this is one of the reasons why the scientific community is freaking out just a little bit. The first question that comes to mind is, what does that mean for us humans? Total annihilation? Now, no need to be this dramatic. The best case scenario, we'd be in for an interstellar type of experience. Roll me in, please. Let's rewind a little bit to understand how this would happen. 45 years ago, a group of scientists began noticing a weird behavior coming from a galaxy far, far away. The galaxy is found 9 billion light-years away, and its scientific name is a mouthful, but let's just call it Super Far Away Galaxy. You might be asking yourself, well, how did scientists observe this black hole so far away if it doesn't emit any light? Good question. That's because black holes gather disks of gas around them, and they emit some of this material into space. These jets can be detected from a distance of millions of light-years. Now, if these hot gas jets are directed towards space, then scientists give these black holes a special name, blazars. A particular blazar has been gaining worldwide attention recently. Long name, but let's just call it Andy. Imagine you're a scientist at Caltech and you're looking at a blazar in your radio telescope and you notice its strange behavior. Its brightness goes on and off, like the ticking of a clock. At first, you don't understand what's happening over there in a distant corner of the galaxy. But then, you realize there must be another black hole circling the first one. In other words, scientists discovered that Andy was being orbited by another blazar, Gomer, and the regularity of their twinkling can only mean they are close to a total collapse.
it gets worse. Each of the two blazars is estimated to be a few 100 million times the mass of our Sun. Have you seen our Sun? It's huge. It's already 333,000 times the mass of our Earth. This means we're destined to face something out of our league. Now, this is not the first time scientists have detected something like this. In September 2015, the LIGO Observatory detected a collision of two black holes. Each of them was as heavy as 30 suns, and an equivalent of 3 solar masses was released once they crashed into each other. And guess what? This gravitational wave passed through Earth at the speed of light, but we really weren't affected by it. Maybe you were sleeping and felt something weird in the air, but nothing significant happened to us as a species or to our planet. But that's because the blast was weak. The thing is, the expected collision between Andy and Gomer will send unprecedented gravitational waves throughout galaxies, and they will reach the solar system. But what is this shock wave actually capable of doing? Well, it could stop our Sun from releasing gas for a few minutes, which means it would stop heating the solar system. So, let's say you were going about your summer day, and out of the blue, the atmosphere froze for a few seconds. Doesn't sound too nice, huh? But that's actually a better possibility than the next one. In one of the worst-case scenarios, a blast from the collision between Andy and Gomer could break bonds between atoms and make everything disintegrate. You, me, your cat, we'd all turn into flying particles floating in the vacuum of space. This may sound scary, but scientists say that an atom is made out of 99% empty space. This means that everyone on this Earth, all 8 billion of us, and everything that exists, planets, objects, animals, are all made up of 99% empty space. So perhaps all that Andy and Gomer would do is separate all of our atoms and desolidify us. Then again, the blast could mess with the fabric of space and time as we know it. You remember Albert Einstein, right? Crazy hair? He's the name behind the theory of relativity. Einstein discovered that time is relative. It's always dependent on the observer. This would mean that time is not the same throughout the cosmos. Why though? Well, because Einstein's theory of relativity is also a theory of gravity. Einstein discovered that gravity is the effect that objects have on the fabric of space-time. Every object that has a mass, including you, me, your cat, and our planet, creates a warp or a distortion in the fabric of space-time that causes it to bend. The bigger the mass, the bigger the gravitational force, and the bigger the distortion on the fabric. It may sound complicated, but hey, this is what creates different perceptions of space and time throughout the cosmos. This is why you'll age differently on Earth and on Jupiter. This is why time passes completely different for astronauts on long missions and for people that remain on Earth. And this is why a collision of two mega blazars could mess with our perceptions of space and time, due to the sheer force of its gravitational shockwaves. Got it? Not to mention that black holes are already a huge warp in the fabric of space-time. You remember that interstellar scene, right? Where the lead character bends the space-time continuum through a black hole? Now, don't try this at home though. As far as we know, anyone who chooses to go inside a black hole has no guarantee of making it home again. Scientists say that this blazar explosion will happen in approximately 10,000 years. But wait a minute. If this blazar lies 9 billion light-years away from Earth, it means that these two black holes should have already collided long before our solar system and home planet were born. You see, the solar system was born around just 4 billion years ago. And since it takes us 9 billion light-years to receive the light emitted from the blazars in the first place, this means that the collapse of the two blazars already took place, and it'll reach Earth 10,000 years from now. This means the shockwaves are already making their way through the galaxies at this very moment. But still, it's not something even your great-great-great-great-great-great-grandchildren will be around to see.
You're traveling through space, trying to get through an especially rough patch. You gotta dodge asteroids, space debris, wandering black holes. Now, it's not an episode of a sci-fi series, at least not completely. For the first time ever, astronomers have found a black hole that's completely alone, drifting through space with no stars or planets nearby. This black hole is about 5,000 light-years away from us in our own Milky Way galaxy. Do we need to look for a hero with superpowers to save Earth? First things first, a black hole is a place in space where gravity pulls so much that nothing, not even light, can get out of this region. The gravity is so strong there because a huge amount of matter is squeezed into a tiny space. Supermassive black holes, hundreds of thousands to billions of times the mass of our Sun, are often found at the centers of galaxies. Most of them stay put or move at a very, very slow pace. But the newly discovered black hole is much weirder than anything we've seen before. First of all, it tries to avoid commitment. It's lonely, with no companion star or home galaxy. An even stranger thing is that it's zooming through space at a speed of 31 miles per second. What might be the reason for this speedy cosmic journey? Let's look at the following imaginary scenario. One day, a really massive star exploded in a supernova. It was the very star that formed our black hole. The resulting blast gave the new black hole a massive kick and sent it flying through the galaxy, starting its unbelievable voyage. Now, it's only one of a few possible explanations, but it sounds quite plausible. I bet you can't help but think, what if this wandering black hole decides to visit our solar system? Are we doomed? Scientists tell you to relax and breathe out. This black hole is very far away, and your chances of ever encountering it are infinitesimal, if any. Plus, this black hole is totally quiet and dark at the moment. One day, it might wake up and start glowing. It'll happen if it begins to eat something. In the near future, powerful new telescopes may find many more wandering black holes like this one. Usually, black holes are super hard to find because they don't give off any light. You can only detect them when they're eating nearby matter. That makes them glow brightly. Or when they have a companion star. In this case, it moves in a strange way, which gives away the presence of a black hole. But this newly discovered black hole is lonely, totally by itself. There's no glowing, no companion star moving hectically. So, how did scientists spot our cosmic wanderer? They used something called gravitational microlensing. That's when the black hole's gravity bends and magnifies the light from a star located behind it, kind of like using a magnifying glass, hence the name. This method allowed scientists to detect the black hole even though it was completely dark. All in all, black holes are fascinating things, and some of them are truly unique, like these biggest black holes ever found. You see, almost every galaxy has a supermassive black hole at its center. They're huge, with masses millions to billions of times bigger than our Sun. One of those is called TON 618. It's a really huge and powerful black hole that's part of something called a quasar, a super bright spot in space emitting incredible amounts of energy. TON 618 is very, very far away, about 18.2 billion light-years from Earth. And it's 40 billion times heavier than our Sun. There are also black holes that feed on their own kind. Black holes are known for devouring anything that gets too close. And this anything can include not only stars and gas, but also other black holes. Scientists witnessed a ginormous black hole at the heart of one galaxy being swallowed by an even larger black hole in another galaxy. It was the first time we detected such an event. The discovery was made using NASA's Chandra X-ray Observatory. One black hole weighs about 30 million times the mass of the Sun, while the other has at least 1 million times the mass of the Sun. Then, there is a bullet-shooting black hole. Apparently, black holes don't just swallow matter, they can also shoot it out. For example, astronomers studied one relatively small black hole, which is about 28,000 light-years from Earth and weighs between 5 to 10 times the mass of the Sun. And they saw how this black hole pulled matter off a companion star and then blasted some of it out in the form of huge bullets of gas. These bullets are super fast. They move at nearly a quarter the speed of light. Some black holes spin incredibly fast, twisting space around them at extreme speeds. One example is a black hole located in the constellation Agila, about 35,000 light-years from Earth. This black hole spins at a staggering speed of more than 950 times per second. If you could place an object on the edge of this black hole's event horizon, it would spin around the black hole at 333 million miles per hour. That's nearly half the speed of light. The smallest black hole discovered so far has been nicknamed the Unicorn. Located 1,500 light-years away from Earth, it's around 3 times the mass of our Sun. This makes it very close to the smallest possible size for a stable black hole. While black holes themselves are far away and difficult to study directly, scientists find new clever ways to study their properties right here on Earth. They've been able to recreate certain features of black holes in the lab. For example, black holes have a gravitational pull so strong that nothing, including light, can escape once it crosses the event horizon. To understand this better, researchers have created an artificial event horizon using fiber optics. They've also been able to simulate Hawking radiation, the kind that likely escapes black holes, by setting up experiments in the lab. These lab-created mini black holes help scientists understand the mysterious properties of real black holes. There are several types of black holes, and each of them is born in its own unique way. Primordial black holes are believed to have formed right after the Big Bang, when the universe was very young. Stellar black holes form when a massive star collapses in on itself. This causes a supernova, where the outer layers of the star explode into space, and the core turns into a black hole. As for supermassive black holes, they're thought to have formed alongside the galaxies they're in. The size of the black hole is usually related to the size and mass of the galaxy. Despite what many believe, black holes don't roam the universe randomly, looking to swallow planets. They obey gravity like anything else in space. So, for a black hole to affect Earth, it would have to be very close, much closer than any black hole is to us right now. Even if a black hole the same mass as the Sun replaced our Sun, Earth wouldn't fall into it. The black hole would still have the same gravity as the Sun, and Earth would continue orbiting it just like it orbits the Sun today. It would get much colder though, so we wouldn't survive such a replacement in any case. But don't worry, our Sun will never turn into a black hole. It doesn't have enough mass to do so. Instead, in about 5 billion years, when the Sun reaches the end of its life, it will become a red giant star. After using up its fuel, it will shed its outer layers, creating a glowing ring of gas called a planetary nebula. What's left will be a cooling white dwarf star. Imagine a powerful giant, like the Sun, clashing with a tiny yet mighty opponent, a small black hole. The collision is imminent, and the fate of the solar system hangs in the balance. Will the Sun be able to withstand the intense gravitational pull of a tiny black hole, or will it be swallowed whole? The answer lies in the forces at play in this mind-blowing cosmic collision, so let's break them down. First of all, what is a black hole? A black hole is a region of space where the gravity is so strong that nothing, not even light, can escape from it. Like a cosmic vacuum cleaner, it sucks up anything that gets too close. It's so massive that it warps the fabric of space-time around it. Black holes are one of the most scary and mysterious objects in the universe, a powerful force of nature that defies our understanding of physics, a true enigma of the universe. Black holes come in different sizes, from small ones that are only a few miles wide, to supermassive ones that are billions of times the mass of the Sun. Most of them are formed by the collapse of massive stars. After the black hole is born, it starts to grow in size by eating everything in its path. And if 2 or more black holes collide with each other, they can merge into one enormous cosmic monster in a terrifying dance. But what about the smaller ones? The smallest known black holes are called stellar black holes. It's a type of black hole that weighs 3 to 10 masses of our Sun, while being very small. It's like taking all the matter in the solar system and squeezing it into something the size of New York City. And yes, it's considered very small. Just for comparison, intermediate mass black holes weigh between 100 to 1,000 solar masses, and supermassive black holes weigh millions or billions of solar masses while being unimaginably huge in size. So, stellar black holes are basically nothing compared to their relatives. Imagine a massive star, bigger than our own sun and with a heart made of nuclear fuel, burning bright and hot. But as the star runs out of fuel, gravity takes over and starts to squeeze the star. The more it squeezes, the hotter it gets, until the star's core reaches a temperature of billions of degrees. Eventually, the core collapses under its own gravity. This creates a massive blast called a supernova. This collapse creates a singularity, which means a point of infinite density and gravity. This point is surrounded by an event horizon, the invisible line beyond which nothing, including light, can escape. And just like that, voila, a stellar black hole is born. Pretty mind-blowing, isn't it? Stellar black holes are the most common type of black holes we know of. These guys can be found all across our galaxy. So, what are the chances that such a little monster will come for our sun? And in that case, what will happen to us? Well, actually, the likelihood of the sun colliding with any black hole is incredibly small. It's almost impossible for it to happen. Even though stellar black holes are the most common type of black holes in our universe, they aren't common at all. The chances of the sun and some black hole crossing paths is so rare, it's basically like winning the intergalactic lottery. Only this win wouldn't be that pleasant. For 2023, the closest known black hole in our solar system is Gaia BH1. It's about 10 times heavier than our sun, and even this one is about 1,600 light-years away from us, which is a quadrillion miles. So, it's safe to say that our sun is not going anywhere anytime soon. But never say never, right? Just like with any astronomical event, we need to understand the different ways something like this could happen. For example, it would be possible if a rogue black hole passed through our solar system, much like a comet or asteroid passing by. Unfortunately, unlike comets and asteroids, black holes are invisible and can only be detected by their gravitational pull. So it's not like we'd see a big, ominous black hole hurtling towards us. Rather, we'd only know it was there if it caused some sort of disturbance in the orbits of nearby objects. So what now? We know that the sun is a massive, luminous star at the center of our solar system. It's about 4.5 billion years old and has enough fuel to last for another 5 billion years. This star is so big that it's hard to even comprehend its size. In fact, if you were to put all the planets in our solar system inside of it, there would still be room for more. And it's so massive that it contains almost 100% of the total mass of the solar system. So it's hard to imagine how some insignificant small black hole thousands of times smaller than this star can devour it. And you're right, it won't. Well, at least not completely. So imagine if a rogue black hole arrived in our solar system and has begun to approach the sun. As it gets closer and closer, the black hole's immense gravity will start to pull the material from the surface of the sun. The sun would start to get stretched and distorted. This is called spaghettification. Imagine a rubber band being stretched until it snaps. That's kind of what would happen to it. This gathered material will form a swirling disk around the black hole, called an accretion disk. As more and more material is pulled in, the disk will heat up and start emitting intense radiation. And as the sun gets pulled in, it would start to release massive amounts of energy in the form of light and heat. The sun would become much brighter and hotter than before. The sun's outer layers would be vaporized, creating a massive cloud of gas and dust that would expand outwards. It would be like a cosmic fireworks show, but with terrible consequences. Even though it would be one of the most spectacular views in the universe, we wouldn't be able to see it. As you might have guessed, the Earth would be in for a really rough time. The intense radiation and solar material would cause massive wildfires, and the intense heat would vaporize the oceans. The Earth would be bathed in a constant stream of high-energy particles, and the atmosphere would be ionized. In short, the chances of any life surviving would be close to zero. And this collision would have far-reaching consequences not only for the Earth, but for the entire solar system. The intense radiation and heat would vaporize everything in its path. All the planets would be destroyed. Now, the Sun being a larger object than a typical star wouldn't be completely devoured by the black hole, but it would be significantly distorted and disrupted. The intense gravity of the black hole would cause the Sun's outer layers to be pulled away, creating a massive blast called a tidal disruption event. But either way, in the end, the black hole would win. It would grow in size, and a new accretion disk would form around it. As we've seen, the collision of the Sun with a black hole, whether it be a tiny or stellar one, would be an epic and catastrophic event. But thankfully, as we've already mentioned, the likelihood of such a collision happening is extremely low. However, that doesn't mean we should stop studying black holes and their potential impact on the universe. The more we learn about these mysterious objects, the better equipped we'll be to understand and predict their behavior. So, let's keep researching, exploring, and observing the depths of space. And who knows, maybe one day we'll come across a black hole that's just too curious and gets too close to the Sun. Let's hope by that time, we will already be living on other distant planets.
The James Webb Space Telescope is an absolutely stunning piece of equipment, which is around 100 times more powerful than the Hubble Space Telescope. And the latter has managed to observe places that are around 13 billion light-years away. But recently, James Webb has outdone itself. It spotted something it wasn't supposed to see. Astronomers using the telescope have detected a supermassive black hole from when our universe was less than 600 million years old. Just a baby. This discovery is the most distant, actively feeding supermassive black ever observed. It's located at the heart of its host galaxy, designated Sears 1019. The black hole is also one of the smallest and least massive ones found in the early universe. It's equal to approximately 9 million suns. It might seem like a lot, but in reality, supermassive black holes often grow to billions of times the mass of our star. But what is so unusual about this find, and why are scientists having a hard time trying to explain it? You see, it's supposed to take way longer than 600 million years for a supermassive black hole to grow to its full potential. It happens when a black hole either feasts on surrounding matter or merges with a larger black hole. Even black holes similar to the one at the center of our Milky Way galaxy, which is almost 4.5 million times the mass of our Sun, are supposed to be seen in the more recent universe. Well, to tell you the truth, scientists have long suspected that supermassive black holes could have existed in the early universe. But this theory has been proven only thanks to the JWST and its infrared eye. It has shown that the black hole Sears 1019 is actively munching on all the matter it can lay its hands on. Such feeding black holes are usually surrounded by swirls of gas and dust falling inside them. Such swirls are also called accretion disks. The gravitational force of a black hole heats this matter, which makes the disk shine bright like a diamond. Sorry, but that's not all. Strong magnetic fields produced in the process channel the matter to the poles of the black hole, and from time to time this matter is blasted out of there in twin powerful jets. They move at a speed that is close to the speed of light, which generates incredibly bright light. By the way, astronomers were watching the galaxy hosting the unusually old black hole as part of the Cosmic Evolution Early Release Synth survey. They saw the galaxy as it was when the universe, which is around 13.8 billion years old now, was a mere 570 million years old. Besides the main character of this video, scientists spotted two other black holes. Those probably appeared 1 in 1.1 billion years after the Big Bang, and 11 ancient galaxies that existed between 470 and 675 million years after the beginning of cosmic history. The coolest thing about all these discoveries is that until recently, all research about things that existed in the early universe was mostly theoretical. But now, with the help of the James Webb Telescope, astronomers can not only see galaxies and black holes at unimaginable distances, but they can also measure them. This isn't the only discovery connected with black holes made recently. For example, not so long ago, scientists saw two stars slow down in their orbits around black holes and concluded it was most likely the result of drag produced by dark matter. It was the first time astronomers might have discovered some indirect evidence that huge amounts of dark matter could surround black holes. Now, about that dark matter. What is it, and what does it consist of? Our universe consists of normal matter, and dark energy. Normal matter, which is everything you can see with your own eyes or with the help of instruments, makes up around 5% of the universe. Since it's such a small fraction of the universe, maybe we shouldn't call it normal? Dark energy takes up around 68%, and about 27% of the universe is dark matter. This dark matter is just one more space thing that confuses scientists to no end. If dark energy is a force responsible for the expansion of the universe, dark matter is supposed to explain how objects work together. Potential candidates for dark matter vary from strange particles to super-dim objects. But even though astronomers can't grasp what exactly dark matter is, they know for sure what it isn't. This matter is dark, so we can rule out visible stars and planets. It also can't be dark clouds of normal matter. Otherwise, scientists would be able to detect it. Dark matter is not antimatter, since astronomers don't see unique gamma rays that appear when antimatter comes in contact with matter. And neither is dark matter gigantic galaxy-sized black holes. In other words, dark matter is still as much of a mystery to us as dark energy. Anyway, back to the potential dark matter discovered around the black holes. If it is confirmed, it'll be a great breakthrough in dark matter research. What helped scientists come up with this idea is that dark matter interacts gravitationally, influencing ordinary matter. So, a team of researchers watched the orbits of two stars decay by about 1 millisecond per year, while they were circling their companion black holes. The scientists concluded that these changes in speed were the result of dark matter generating friction and a drag on the stars. With the help of computer simulations of the black hole systems, the team tested a model widely known in cosmology. It's called the dark matter dynamic friction model, and it predicts a certain loss of momentum by objects that are gravitationally interacting with dark matter. And guess what? The simulation matched these predictions. The results of this research helped to confirm a theory that had existed for a long time, that black holes can actually swallow dark matter that comes too close. As a result, dark matter gets redistributed around black holes, creating areas with different densities, which can influence the orbits of surrounding objects, like the stars we've been talking about. Speaking of black holes, there's a theory that primordial black holes could actually be dark matter. This type of black hole is hypothetical since scientists have never got any real proof of their existence. Such holes are insanely old and quite tiny, by black hole standards, that is. Astronomers believe they could appear several milliseconds after the Big Bang. At that time, stars and galaxies weren't born yet. It means primordial black holes probably witnessed the entire history of the universe. By now, the smallest primordial black holes have most likely evaporated away, but some bigger ones can still be scattered out there in space. If primordial black holes indeed existed, they could appear because in some regions of space, it was hotter, other regions were cooler, and some areas were extremely dense. Scientists believe these dense spots could collapse into primordial black holes. The most curious thing, though, these holes might be so small exactly because they popped up right after the Big Bang. The thing is, the longer it took a black hole to appear, the larger it was. The mass difference between older, smaller, and younger, bigger black holes was incredible. Compare the mass 1,000 times greater than our sun's and that of a pea. There you go. Anyway, the idea of the connection between primordial black holes and dark matter, or rather, the idea of them being the same thing, remained unpopular for decades. But recently, scientists have realized there are many more black holes in the universe than they used to think, and it means that the theory might actually work. And the vast and still hidden from us population of Big Bang black holes could not only make up but be dark matter. After all, astronomers haven't discovered a single dark matter particle yet, even after decades of searching.
To see one of the most significant astronomical events of all time, we go to South America. In the Atacama Desert, Chile, we find the most advanced technology for space observation. Here, the Royal Astronomical Community members watched for 6 months as a black hole simply absorbed a massive star. By the way, these are the same scientists who proved that in the center of our Milky Way galaxy, is a supermassive black hole, and even took a photo of it. For the first time in history, this incredible event happened very close to Earth. Well, the distance of 215 million light-years is considered quite close in astronomy terms anyway. Light from this event reached our planet in September of 2019, and even the most experienced scientists dropped their jaws in surprise. Imagine a star the size of our Sun, about 860,000 miles wide. Such stars have enough weight to create a strong gravitational field holding many planets in their orbit. And now, let's place a giant black hole next to it. The hole is absolutely black, shaped like a disk, and weighs 1 billion times more than this star. The force of its gravitational field is incredible. Nothing can leave its gravity force. Objects that can move at the speed of light will still fall into this black abyss. Even light itself cannot escape its boundaries. As soon as a star enters the gravitational field of a black hole, it has no chance. At first, it tries to resist the pull of the black hole. Still, the star's outer layers begin to stretch toward the black hole, just like spaghetti. This is due to a powerful force of attraction. If you had the opportunity to extend your hand toward the black hole, you would see your fingers begin to stretch and elongate. This is because the force of attraction increases with every inch. Therefore, it acts stronger on your fingers than on your arm. That's why this process of pulling objects into a black hole is called spaghettification. The first thing to be sucked into the black hole is the star's crown. This is the outer shell of the star, which consists of hot plasma. You may notice how the star begins to shrink in size. This is because that plasma makes up most of the visible sun. When this hot plasma spaghetti reaches the black hole, it may appear to remain on the disk's edge and continue to orbit the black hole. But in fact, there is no turning back anymore. The star's particles have already hit the event horizon of the dark abyss. The gravitational field of a black hole bends light around its edges, so the event horizon looks a bit like a croissant for the observer. Boy, lots of food metaphors here. I'm getting hungry. You may also notice a kind of chaos in this ring, as if some light particles are moving in one direction and others in another. This happens because of a mirror effect. But you can be sure that whatever reaches the event horizon will, sooner or later, be pulled into the singularity, or the black pearl of the black hole. Another illusion you spot is the star particles in the event horizon moving slower. The truth is that supermassive objects like a black hole curve space-time around them, and the more massive the object, the slower time flows near it. If you hang one watch beside a black hole and another on a wall in your bedroom, you will see that the second hand in the first watch barely moves, while a whole day passes on Earth. As observers, it seems to us that the particles of light have slowed their movement, but in fact, they may have already been absorbed by the black hole ages ago. Now, massive streams of red-hot plasma splash into space, just like spaghetti sauce. When a black hole has absorbed star material, it emits powerful rays of energy at a rate of about 6,200 miles per second. This release of energy is accompanied by an intense flash. It's thanks to this flash that scientists can even detect this process in the first place. This phenomenon can be observed when a supernova explodes. When nothing remains of the star's body, we can still see stardust and other particles in the black hole's event horizon. Kinda like the Parmesan cheese sprinkled on the spaghetti. Hey, stop me if I'm taking this too far. When the process of spaghettification is completed, about half of the star's weight has been thrown into outer space as dust and glowing particles. The other half was entirely absorbed by the black hole. The scientists observed this process for almost 6 months. But what would be more interesting is to dive into a black hole yourself. Well, we can't do that yet, but we can simulate this process. Here's a little drone, our metal friend, kinda like a meatball. No, I haven't had lunch yet. Right now, it's at a safe distance from the black hole, the length of about 3 widths of the event horizon. Objects at this distance can orbit the black hole safely. A little closer, and it'll be swallowed up by a dark infinity. So, our destroyed star could have safely existed at this distance. Moreover, planets can live at this distance. And if there is a suitable source of light and heat somewhere nearby, life can exist on these planets too. But our goal is the singularity, and we guide the the drone, closer to the event horizon. After a few minutes, the force of attraction begins to strengthen, and the drone starts to stretch like spaghetti. When it begins spinning around the black disk, it means it has reached the event horizon and has started its descent into the black abyss. Now let's look at everything from the drone's perspective. All the light from the stars that it sees becomes blue. This is called gravitational blue shift. As it falls into the black hole, its gravitational field pulls the photons of light down, giving them energy. Their wavelengths grow shorter, so the red photons change into blue. The drone continues to fall and is already completely hidden from our eyes. And all that the robot sees is a bright, thin blue beam. Now it's in complete darkness. There's absolutely nothing here, not even time. Here, time goes so slowly that our entire solar system could grow old and cease to exist during a minute spent in a black hole. But our drone will live until its battery is empty. Hey, the drone sees a small bundle of light again, and it's getting closer and more prominent. Now the drone will experience the same fall, only in reverse. Once the drone leaves the singularity, the heart of the black hole, it will be on the event horizon once again. The light from the stars gradually changes from blue to red. Then the drone is thrown into outer space, perhaps in some faraway galaxy. Well, returning from a black hole is just a theory. Some people think that black holes are a kind of wormhole that can lead us to distant places in space. But so far, these theories are considered fiction. Black holes are quite challenging to detect. The problem is they are, black, just like space. They don't emit light like stars, so they can only be detected by gravity anomalies. Despite this, scientists believe there are a vast numbers of black holes in our universe. They're born when a massive star collapses under its own weight, and given the infinite number of stars in the universe, black holes are probably a common phenomenon. Scientists believe black holes have their own lifetimes. This is because of Hawking radiation. A black hole loses mass, and so, to continue existing, it has to absorb massive objects, like the star we just watched. But if the black hole lives in deep space, it has less to absorb and will most likely begin to shrink until it just disappears. Like this plate of spaghetti.
Black holes, the most terrifying, mysterious, and fascinating objects in the universe. Eternally hungry, they eat everything in their path and are constantly expanding. But how small and how big can a black hole be? Let's find out. It's not very easy for a black hole to be born. Most often, they're just a result of a massive star ending its life cycle. If you take a star and squeeze it very, very hard, at some point it cannot withstand the pressure anymore. So it collapses and turns into a black hole. For example, we can create a black hole by shrinking the sun to about 1.8 miles, or squeezing the Earth into the size of a pea. Either way, in the end, we get a mysterious, dark object with incredible mass and gravity. Unlike stars and planets, black holes have no size restrictions. They grow when they eat the matter around them, but how much does their size vary? For example, can they be very small? Theoretically, yes. There may be black holes with a diameter of 1 atom, or even less. They're called primordial black holes. They may or may not exist, and if they do, they're probably the oldest objects in the universe, older than the atoms themselves. They would have formed right after the Big Bang, a long time ago when the universe still had an incredible density, a huge amount of energy, and in general was like a boiling broth. any particle that was slightly denser than its neighbors could form a black hole. And the smallest of them would still weigh trillions of pounds. Those that were the size of atoms would weigh as much as a big mountain, and those that would weigh as much as the Earth could be a little bigger than a coin. But even if they exist, they're pretty harmless. The temperature in them would be so many times hotter than in our sun, so they would evaporate pretty quickly after their birth. Now let's check out the black holes we know and saw. The first ones are called stellar black holes. Usually, they weigh tens of solar masses, which doesn't seem like much until you remember that the sun weighs nonillions of pounds. Don't even try to imagine this number. It has 30 zeros. The smallest black hole known to us is about 2 to 4 times heavier than the sun. It's a lonely hole that wanders through space in search of prey. The one that's closest to us is called Gaia BH1. It weighs about 10 times more than the sun and can reach many miles in size. And the farthest one is called M33X7. It's somewhere around 3 million light years away from us, and right now, it's eating a blue giant that's several times bigger than our sun. Now, let's move to the so-called intermediate mass black holes. You see, just eating a few stars isn't enough. To become larger in size, black holes must either absorb a lot of stars or, more often, merge with another black hole. One of the first intermediate mass black holes that we found was born this way. It weighs 142 times more than the sun. It's even larger than some counties on Earth. Recently, we discovered 2 black holes in a galaxy 17 billion light years away from us. One day, they'll merge, but right now these guys are spinning around each other in a crazy dance. And while doing that, they release a crazy amount of energy. It may seem scary, but it's nothing compared to what comes next. Let's move to some serious stuff. Supermassive black holes. Giant, inexplicable monsters that are millions of billions of times bigger and heavier than our sun. But how did they become so huge? The universe is about 14 billion years old. The black holes grew very slowly, so they couldn't have time to eat so much matter or merge with each other so quickly. So maybe they were also born from the stars, but very, very big ones. Quasi-stars. To imagine their scale, let's take, for example, the red supergiant Stephenson 218. Compared to this star, our sun is just a grain of sand, even smaller. And Stephenson 218 would be a grain of sand next to a quasi-star. We don't know if they really existed though. They could have formed after the birth of the universe. They could be so big that their core collapsed under their own weight before they even formed. And if that's the case, a small black hole would have appeared in the center of this quasi-star. Now, the frenzied gravity of the black hole held the star together and ate it at the same time. The temperatures were huge, so the star remained stable. And they would live like this for millions of years, until the black hole would grow to enormous sizes. Most supermassive black holes are located in the centers of galaxies. You might think that our galaxies orbit around them as we do around the sun, and that one day we will inevitably all be dragged inside it. But don't worry, that's not the case. Although these guys are incredibly massive, they're not very large in diameter. They can't swallow entire galaxies. For example, in the center of our Milky Way, there's a black hole called Sagittarius A. It has 4 million solar masses, but it's still quite small in size, only 17 times larger than the sun. And yes, it's still considered small. If we had replaced the sun with this black hole, it wouldn't even have reached the orbit of Mercury. Sagittarius A is actually pretty nice and calm. Yes, it still swallows giant stars, but it's definitely not a threat to us. But not all of them are like that. For example, a black hole in the galaxy BL Lacertae devours a huge amount of gas and dust. If we were somewhere near it, it would look 115 times larger than the sun, and we would have burned up just getting close to it. Do you remember that first black hole we ever captured in a photograph? It's located in the Messier 87 galaxy, and it may look small and cute in the photo, but in reality, it's capable of absorbing our entire solar system up to the Orion Belt, and even further. Well, now that we've discussed the terrifying size of supermassive black holes, it's time to move on to the real titans of the universe. Ultramassive black holes. Terrifying, unimaginable giants. The largest objects that have ever existed and probably will exist in our world. Their masses exceed the mass of the Sun by tens of billions of times. Their gravity becomes so strong that they create quasars around them. Disks that shine brighter than thousands of galaxies combined. Remember, we talked about the fact that supermassive black holes aren't able to eat galaxies? Well, these guys devour not only their host galaxies, but literally everything on their path. The ultramassive black hole at the center of the galaxy OJ287 has 18 billion solar masses. It's so gigantic that it has another black hole orbiting it. It would also easily fit not one, but 3 solar systems inside of it. And now, finally, we've come to the largest object in the entire universe. TON 618, the almighty destroyer of worlds. A black hole that has eaten far more than one galaxy. Its mass exceeds 66 billion solar masses, and it could fit 11 solar systems inside of it. The quasar around TON 618 shines brighter than 100 trillion stars. Its light is so powerful that it has even reached us, even though we're at a distance of 18 billion light years from it. And the creepiest part is, this isn't even its true size. This is what it looked like around 10 billion years ago. Since TON 618 is so far away, its light reaches us for a very long time. That means what we see is how this black hole looked after the universe was born. But what does it look like now? We have no idea, but it's probably millions, billions of times bigger.
So you're standing on a diving board in the middle of an open space. You look down, but that's not a pool. It's a giant black hole. Well, what the heck? You start swinging and then you jump. The gravity of the black hole grabs you, and you pick up speed. Just a little more, and you'll enter the dark abyss. But you're not afraid. You're sure you can survive the fall into the black hole. Besides, you have a clear goal to travel through time. But first, let's figure out how it works and why time stops near a black hole. This is the space-time grid. It's what our entire universe is made of. And just like a regular grid, it sags if you put something heavy on it, like me. For example, let's put the planet Earth here. You see a little funnel that is formed around the Earth. And if you put a small ball next to the planet, it'll roll into the funnel. That's how gravity works. The heavier the object, the more it bends space-time. By comparison, here's the Sun. It's almost 333,000 times heavier than the Earth, so it makes a really big funnel. So big that all the planets in our solar system move around that star inside that funnel. So now, let's put a black hole on a space-time grid. Its centers are infinitely heavy, so they create a limitless deep well. And anything caught in the black hole's gravitational field can never leave it, not even moving at the speed of light. Okay, their gravity is infinitely strong, but why do they slow down time? It's all about the speed of light. According to physics law, the speed of light must be the same at every point in our universe, even in a black hole. So, for our experiment, we take this ball, a photon of light that can travel 671 million miles per hour. You could get from Earth to the Sun at that speed in 8 minutes. That's how long it takes light to travel from our star to our eyes. So, when you're looking at the Sun, you're looking back in time 8 minutes ago. By the way, don't look at it directly. Now, the critical thing to remember here is that velocity consists of 2 physical quantities: space, miles, and time, hours. We'll use that later. Now, let's look at the black hole in our space-time grid. In 3-dimensional space, it appears like this. But if we assume that space is 2-dimensional, our grid looks like this when viewed from above. Just a lot of squares.
And this is the black hole right in the middle. If you look at the grid from the side, you'll see a straight line. And the black hole here looks like a pit, or like an endless well. Now, let's follow our photon of light in three-dimensional space. Here, it's moving toward the black hole, and then it falls into the well of the black hole, and it continues its motion at a constant speed. Now, the side view. Again, the photon moves from left to right and then falls. Its velocity doesn't change. The problems begin if you look at the experiment from above. When the photon of light moves in the distance of the black hole, its speed is stable. But then it goes down into the well. First, it slows down and then it just stands still. But it's moving downwards. The photon moves in an arc down the well in the lower dimension without changing its speed. But in the higher dimension, it traveled a minimal distance at the same speed. Usually, this would mean that the photon was moving at a low speed in the second case, but not in the case of the speed of light. Remember, it must be the same at every point in the universe. The number 671 million miles per hour shouldn't change. So, we change the very parameters of that number, time. Time itself must slow down so much that this slight movement of the photon, when you look at it from above, was at the same speed, 671 million miles per hour. But if you go down and look at this well much lower, you see that its walls are almost vertical. So, a photon of light would be moving in a vertical trajectory. That means that if you look at it from above, the photon will just be standing still. Again, its velocity can't change, so time will vary. At that point, it should just stop. This is what happens near a black hole. Now, if you look at a black hole, you can see this effect in action. It swallows up the light around it. But as for an observer, it seems to you that the light stays in orbit around the black disk. In fact, at that moment, the photons are still moving at the speed of light inside the black hole. It's because time has slowed down there so much that you feel like the light has stopped there. This disk is called the event horizon, the point of no return, the last stop before you go into the black abyss. And at the very center of the black hole is the singularity. This point of space is so dense that if you try to describe it with any numbers or physical quantities, they would all tend toward infinity. Simply put, all the laws of physics we know just stop working here. So scientists can't say exactly what awaits you in the singularity. Before you make that jump into the black hole, let's drop a space probe there with a blue light that flashes once per second, and let's attach giant clocks to it. You see the probe falling into the black hole, gaining speed, but then it starts to slow down. Moreover, the probe flattens out and seems to spread out around the black hole. And then you notice that the blue beacon on the probe has changed its light. It now flashes as red. It's because the light is a wave. Blue is a truly short wave with a high frequency. But the black hole's gravity acts on this wave, stretching it out. The light waves get lengthened and become broader and less frequent. The new wavelength and frequency match with the red color. It's called redshift. Also, the probe blinks now not once a second in short beeps, but lights up and goes out for a long time. It's because of the time warp. If you, as an observer, look at the clock on the probe, the second hand there barely moves. However, the clock on your hand works as usual. But if you could be in a black hole, time would seem normal to you, and the arrow on the clock would move as it did before. But the hands on the clock outside the black hole would move like crazy to you. That's because time goes much faster outside the black hole. Oops, your probe just got ripped apart. That's because of the substantial difference in gravity that acts on the probe. The black hole's gravitational force increases with every foot of approach. That is, if you were to extend your hand toward the black hole hard, the gravity on your fingers would be much stronger than on your shoulder. This force would cause your fingers to lengthen, simply like spaghetti. That's why many people think it's impossible to survive falling into a black hole. But scientists think you could survive without a problem. Hey, maybe they should jump first just to make sure. The thing is, you have to pick a black hole as big as possible, like the ones at the centers of galaxies, for example. That bright spot at the center of the Milky Way also has a black hole. It's about 1 million times heavier than the Sun. And this is the Messier 87 galaxy, one of the most massive galaxies among our neighbors. In 2019, humanity got its first ever photo of the black hole at the center of this galaxy. It's about 6.5 billion times heavier than our Sun. So, it's the perfect place to make your jump into a black hole finally. Let's go. At first, you feel a strong acceleration as the incredible force of gravity grabs you. But in the case of a supermassive black hole like this, the gravity doesn't change as dramatically. That's because of its size. Right now, the gravitational force on your legs is about equal to the gravitational force on your head, so you don't turn into spaghetti, and you feel comfortable. You see that the light from the stars and all the space around you has begun to shrink at a certain point. It means that you have already passed the event horizon and are now moving toward the black hole's heart. As a result, the light of the universe becomes a small dot for you and then disappears altogether. If we look at our space-time grid, you're already falling into a well. Time is completely stopped for you. However, the rest of the world continues to move steadily through time. If you could now look at the Earth from a black hole, you would see a time lapse, an accelerated video of how the months and years go by on our planet. If you had a jetpack that had an incredible engine to pull you out of the black hole, then you can make a jump forward in time. In 1 second, centuries on Earth could pass in the heart of a supermassive black hole. But this only works one way. You can't go back in time. But for now, you keep falling into the black hole. Beyond that, no one knows what'll happen to you. We only have theories about wormholes and white holes that might transfer you somewhere else in the universe. So, enjoy your trip, and just think about all the frequent flyer miles you're racking up. Now, I don't want to spook you, but there's a chance that our entire Milky Way galaxy is located in the so-called space void. It's a region where there's relatively little matter compared to other corners of the known universe, and it's much less dense than it is elsewhere in the universe. In other words, we might exist in an air bubble in a cake. If that's true, it would mean that we're even lonelier than we thought. In our universe, all the galaxies are constantly moving away from each other. In order to understand how far they move away, scientists use something called the Hubble-Lemaitre constant. It's like a speedometer, but for galaxies. However, there's a cosmic mystery called the Hubble tension. It's challenging what we know about the universe's expansion. Scientists used to consider the Hubble-Lemaitre constant a reliable guide, but our recent observations question this reliability. The speeds we see in real life don't match up with the distances we calculated and expected. They aren't sure why these measurements don't add up. Researchers followed the moves of supernovas and saw that the universe seems to expand faster around us than it does overall, as if it's actively avoiding us specifically. After considering this, they began to assume that we might all live in a cosmic void. Cosmic voids are vast, empty spaces between galaxies, kind of like between my ears. They make our entire world look like a big sponge. Now, let's go back to the beginning, just a fraction of a second after the Big Bang. Right after the beginning of everything, the universe was a hot, compressed plasma. It only had very tiny variations in density, called quantum fluctuations. After the Big Bang, the universe began to expand. Those quantum fluctuations grew together with it, creating regions of varying matter density. Because of that, the universe didn't expand everywhere uniformly. Instead, little claps of matter began to gather together over a long period of time, creating massive structures, galaxies. Galaxies are arranged in huge walls and filaments, with enormous gaps in between. And these gaps are voids, also known as dark space. Now, these voids aren't truly empty. In fact, they actually hold more than 15% of the amount of matter found on average throughout the entire universe. They still contain gas, dust, dark matter, and even stars and galaxies. However, they have less density than regions with galaxies, about a tenth of the average matter density, which is why we consider them nearly empty. Usually, they'll have a diameter ranging from about 30 to 300 million light-years. That is an enormous distance, even on a space scale. For comparison, most planets and nebulas we've found so far have a distance of hundreds and rarely thousands of light-years away from us. In the case of voids, if you were in the middle of one, it would just look like seemingly eternal darkness. The closest stars would be so far away that they would be almost invisible to you. Some of them are especially large. They're known as supervoids. The largest known one was creatively named Giant Void. Ooh. It's so big, it's impossible for us to even imagine. 1.5 billion light-years away, with a diameter of 1 to 1.3 billion light-years. Yeah, it's basically a big dark vacuum. But even this giant vacuum isn't entirely empty. The giant void houses 17 separate galaxy clusters within its expanse. However, it might not be the biggest emptiness in our universe. There's this thing called the CMB cold spot. It's this unusually large and chilly area of our universe that we saw through the microwaves. It really stood out on the map of our universe with its unexpectedly low temperatures, and scientists have spent many years trying to figure out what the thing is. In 2015, scientists proposed that this place might be a supervoid, and probably the largest one ever. Being even more original with this one, they called it the Great Void. If it's true, this place would be an emptiness of about 1.8 billion light-years in diameter, about 1,000 times larger than typical voids. Not everyone thinks that's possible, so scientists keep arguing over this one. There's another interesting theory going about this place. One researcher suggested that this place might have been a trace on our collision with a parallel world. It's a pretty bold hypothesis, but unfortunately, there's no way for us to confirm or deny it with our current technologies. In any case, as the universe expands, these voids will grow, and the walls connecting galaxy clusters will stretch and break. Eventually, the voids will merge, leaving gravitationally bound galaxy clusters as islands in the expanding emptiness. In other words, sooner or later, the great emptiness will consume everything in our world. So, it turns out we might be a rare occasion in a supervoid, one of the 15% of matter. This would explain why we're surrounded by relatively few galaxies. This discovery, if true, challenges the standard model of cosmology which we created with Albert Einstein's help. It would mean that gravity in general behaves differently than what we expected. According to the standard model, such a significant underdensity shouldn't exist. Because of that, scientists will have to explore and consider this idea thoroughly. It might just challenge our very basic understanding of physics. The scientists call this the local hole. The discovery of the local hole may hold clues to explaining the Fermi paradox. Maybe in this specific part of the universe, where we hang out, the chance of intelligent life developing anywhere nearby is very low. Perhaps all of the sentient beings hang out somewhere beyond our supervoid. But that doesn't mean we should lose hope, or that life anywhere nearby is impossible. In fact, life in the universe might be much more common than we previously thought. We know that the inner planets, like Mercury and Venus, are inhospitable due to extreme conditions. However, Venus looks interesting because even though it's a crazy toxic planet, scientists believe that it was very Earth-like in the past. It could have even hosted life. Unfortunately, it was too close to the Sun and all the nice conditions evaporated over time. But there's a possibility of microbial life surviving in its high-altitude clouds. Mars, a cold desert, also might have been a friendlier place in the past with rivers and lakes. Though now it lacks a protective atmosphere, ancient life might have existed there. In that case, it would leave potential fossils and underground microbes could still survive. We've discovered some signs of them, but are still debating whether this stuff was truly organic or not. The gas giants, like Jupiter and Saturn, and ice giants are not ideal for life, but their moons offer hope. Europa has an ocean beneath its icy surface, making it a potential hotspot. Enceladus releases water into space, carrying complex molecules that hint at interesting possibilities. And Titan is especially unique. It has liquid bodies on its surface. Rivers and lakes have hydrocarbons. While its frigid temperatures aren't great for life, scientists ponder if it might host life with a different kind of chemistry. However, it will take us decades to check all these celestial bodies and study them properly. We haven't sent anything so far since the times of Voyager 2, but if we're lucky,
We might explore our solar system during the 21st century. We might explore our solar system during the 21st century. In any case, there's a lot of potential for life even in our solar system alone, not even mentioning all the planets and galaxies we found nearby. Our estimates suggest that the observable universe, the one we can see, might host around 5.3 trillion habitable worlds. One of the most likely candidates so far is Kepler 186f. It's a potential Earth-like planet, just 10% larger than Earth. This planet orbits a red dwarf star, which is a star a bit dimmer, colder, but more long-living than our Sun. And it's only about 490 light-years away, which may sound like a lot, but remember what distances we've discussed with supervoids. So even if we really are in a supervoid, we're still lucky to have many galaxies and planets around. And if one day we'll find a way to travel through the universe, leaving the local hole probably wouldn't be a problem.
You're traveling through deep space, circling stars and entire galaxies. Whoa, looks like this multicolored nebula will soon collapse under its own weight and explode like a supernova. Now let's carefully circle this black hole. Try not to get caught in its gravitational field, or it'll swallow you like a space monster. Wait, what's that strange structure right there? It's a glowing wall. And if you look closely, each glowing dot is an entire galaxy. That wall has about 100,000 of these galaxies. The Milky Way has 100 billion stars. So this wall holds a quadrillion, that's 10 followed by 15 zeros, of stars like our Sun. This giant structure is called the South Pole Wall. It's located about 500 million light-years from Earth. By comparison, the closest star to our home is Proxima Centauri, and it's about 4.2 light-years away. Rockets can cover that distance in about 73,000 years. So the journey to the South Pole Wall may take longer than our solar system exists. And this wall is simply gigantic, even on a cosmic scale. It's about 1.37 billion light-years long. To give you an idea of how large that is, the Milky Way is only 100,000 light-years wide. But you can't see this wall even with the most powerful telescope. The problem is that the Milky Way itself obstructs your view. It's so bright that it's hiding this wall. It's like trying to look at the starry sky in a metropolis. The light pollution won't let you do that. Scientists have been able to detect this galactic wall by measuring redshift. We know that all objects in the universe are moving. They spread out from each other as a result of the Big Bang, which happened billions of years ago. And when galaxies move, their light waves change slightly. By measuring this change, we can understand what the object is and how it moves. And this wall isn't even the largest in our universe. This is the Hercules Corona Borealis Great Wall. It's a giant flat superstructure about 10 billion light-years wide. That's around 10% of the entire observable universe. And it's also a wall. That is, a cluster of galaxies. We were able to detect this giant structure by gamma-ray bursts. It's the brightest electromagnetic event in the universe. You could even see it in the far reaches of our universe. Such bursts are a very rare event. In the Milky Way, for example, it happens once every few million years. If we notice many such bursts in a short time from the same place, it means that there are many objects like the Milky Way in that place. So, there are a lot of galaxies out there. Another unusual giant structure in the universe is the huge, large quasar group. It's about 4 billion light-years across. So it takes a photon of light almost as long as our planet has existed just to get from one side of the structure to the other. And if you put the huge, large quasar group on the scale, it would be 6.1 billion times heavier than our Sun. Scientists have found that there are at least 73 quasars in that structure. These are some of the most unusual objects in the universe. They are the active cores of galaxies. At the center of a quasar is a supermassive black hole. This giant eats up the matter around it. A wild force of gravity twists the matter around the black hole, forming a disk. And this disk is the source of the strongest radiation out there. By comparison, the radiation from a single quasar is tens or hundreds of times stronger than that of all the stars in our galaxy put together. Because of such strong radiation, we can detect quasars, even at very long distances. That's why they're also called beacons of the universe. Scientists use quasars to study the universe and the movement within it. One of the most distant quasars from us is about 13.1 billion light-years away. This makes it one of the oldest objects in the universe. It appeared about 690 million years after the Big Bang, and it's almost 3 times older than our solar system. It's still glowing with extreme brightness, about 4 and 14 zeros times brighter than the Sun. Scientists explain that at the center of the giant is a supermassive black hole, 800 million times heavier than the Sun. All these giant structures are just building blocks of our universe. Look, this is our solar system. Now, zoom out a little, and this is where our home star is in the Milky Way galaxy. Zoom out again. Here's a local group of galaxies. All the bright spots here are galaxies. Here's Andromeda, and here's the Triangulum galaxy, plus a few dozen other slightly smaller galaxies. They're all gravitationally connected. The size of this structure is about 10 million light years. That's 100 times the width of our galaxy. Zoom out, please. This one is the Virgo supercluster. It's 20 times larger than the local group. There are about 30,000 different galaxies, and the mass of the whole thing is about 1 in 15 zeros solar masses. Zoom out again. Laniakea. This structure is almost 3 times larger. It includes the Virgo supercluster and other smaller clusters. And there are about 100,000 galaxies here. It's not over yet. Zoom out one more time. Here's the Pisces-Cetus supercluster complex. This giant galactic structure contains about 60 clusters of galaxies. So there are more galaxies in it than grains of sand in the desert. You know what to do. Zoom out! Phew! This is the observable universe. There are over 500 billion galaxies. And the stars? Well, there are about 1 billion trillion stars. The observable universe has its own structure. Clusters of galaxies form chains and walls, as you've seen before. But these strands are separated by huge regions of absolute emptiness. These areas are called voids. In these places, there is no matter at all. There are fewer molecules in the voids than in an empty room. One of these voids has a very mystical reputation. It's the Eridanus supervoid, or the cold spot. It appeared here only 380,000 years after the Big Bang. It's almost 1 billion light-years wide and could hold hundreds or thousands of galaxies with trillions of stars. Some scientists believe that this cold spot may have been the result of the largest collision ever, a collision of universes. There's a theory that our universe is some kind of bubble, a huge sphere that contains all these walls and chains of galaxies. Now imagine that there's an infinite number of these bubbles. They could be parallel worlds or different universes. Many years ago, one bubble came close to the bubble of our universe. Their walls touched, and the 2 universes connected for a while. It's like 2 drops of water coming together. But that universe kept moving. The area where the bubbles joined became thinner and thinner until that connection broke, and the 2 bubbles detached from each other. At this point, the second universe ripped some of the material out of our bubble. All those galaxies that used to fill the Eridanus supervoid ended up in a parallel universe. Scientists supposed we might travel through other bubbles. Flying to the supposed wall of our universe would take forever, and then it would take even longer to fly through inter-universal space. So we have to use portals, or wormholes. Here's how it works. Imagine a piece of paper with point A on one side and point B on the other. Instead of moving all the way across the sheet of paper, we just fold the sheet so that point A is right above point B. All that's left to do is make a small hole, and the journey takes only moments. Some scientists believe that such shortcuts through universes lie inside black holes. But how do you survive falling into a black hole? You just have to pick one that's big enough. It's all about gravity. Imagine you're falling into a black hole right now. The closer you get to it, the stronger effect it has on you. It intensifies with every inch. At one point, the gravitational force that affects your head is much stronger than the one that affects your feet. Then you turn into spaghetti. Yum. But if you choose a supermassive black hole, like the ones at the centers of galaxies, the gravitational force in them increases gradually. They can be millions of times heavier than the sun and much bigger, but the gravitational force on your head and your feet will be almost equal, and you will still feel comfortable. Who knows? Maybe if you managed to survive a fall into such a massive black hole, you'd find yourself in a completely different universe where different laws of physics apply. But so far, this is just a theory.
There are probably 36 other civilizations hanging out in the Milky Way, and over 170 billion galaxies, give or take, in the observable universe. Conditions for life are all over space. So, where is everybody? Nuclear physicist Enrico Fermi came up with this exact same question during a lunch break with his colleagues in 1950, leading to one of the most unsettling paradoxes in the universe. Even though there's a huge probability of extraterrestrial civilizations existing, we still haven't found any clear evidence of them. One possible explanation comes from the zoo hypothesis. It suggests that advanced extraterrestrial societies exist and know exactly who we are and where we are, but intentionally choose to stay hidden. They're just observing human quirky behaviors, as if we're in some kind of a cosmic wildlife park. But their intentions could be much darker. If you're a Star Trek fan, you probably remember the main rule for Federation members. Starfleet officers shouldn't contact species that are not advanced to avoid messing with their development, even if it means risking their own lives. Now, even though it's fiction, this rule perfectly captures what the zoo hypothesis is all about. Beings from other corners of the universe see our planet as a cosmic zoo with one-way bars. They can watch us brushing our teeth in the morning or walking our dog, but we can't catch a glimpse of them. In this theory, non-terrestrial life forms deliberately keep their distance from us, sticking to a hands-off policy agreement in the vast cosmic neighborhood. It's like those super smart beings agreed that we needed to have the freedom to shape our own future and destiny, following our own path of development without external contamination. The idea is that these super advanced civilizations could be like, 500 million years ahead of us, which would explain why we haven't seen any signs of them. And maybe it's better this way, as humans could eventually be destroyed or even assimilated by this new cosmic power, Independence Day style. As much as things like going to an art museum might be interesting to us, extraterrestrials probably wouldn't be too thrilled watching us stare at the Mona Lisa painting for hours. Interplanetary cultures might be more into buying tickets to quietly observe how we're developing new technologies, such as ultra-modern satellites. According to the zoo theory, they can't reach out to us until we hit a certain level of development. So improving our technology and wisdom could be the only way to show them that we're mature enough and don't need their spaceship parenting anymore. There are a couple of reasons why it's hard to buy into the zoo hypothesis. Extraterrestrials might not visit or reach out because we're not all that advanced. But it is tough to explain why they keep ignoring all our attempts to communicate. Even if the zookeepers try their best not to interfere with animals' lives and behaviors. I bet they couldn't just ignore a bear speaking in loud and clear English about its desire to communicate. So that's pretty much why humans keep trying and trying to provoke some reaction from inhabitants of other planets using radio signals. In 2017, in a valley 8 miles southeast of the Norwegian city of Tromsø, a radar antenna transmitted some specially composed electronic music to potential intergalactic listeners. The target audience was in GJ273, also known as Lyton Star. It's a runty red dwarf located 12 light-years from our solar system. Since radio waves travel at the speed of light, we'll have to wait more than 2 decades before looking for a reply. But the main problem with radio waves is that we're kind of in the dark about where to look, and civilizations might be as far as 17,000 light-years away. Plus, we don't know which radio frequency extraterrestrials use to chat. Now here on Earth, we use the radio spectrum to send signals into the universe, assuming that what works for us might be a common method for other civilizations. But in fact, it could be considered a somewhat old-school technique for other beings. That's why current projects are now looking for technosignatures, which are signs of technological activity from extraterrestrials, like city lights, solar panels, megastructures, or artificial satellites. Another potential clue is to study the atmospheres of planets orbiting nearby stars, as an advanced civilization might be altering its atmosphere with different gases, making it detectable. Despite decades of observations, there is still no definitive evidence that advanced extraterrestrial civilizations are out there. But that doesn't mean they don't exist. Even by expanding search fields, we're talking about odds much slimmer than hitting the jackpot, with a roughly 1 in 3 billion chance of finding an advanced civilization within a given distance from Earth. Maybe space creatures are responding to our communication attempts, but in a way that we can't understand. The universe has been around for more than 13 billion years, while humans showed up just 200,000 years ago. And this is about 0.01% of the universe's age. It's like we're still learning to talk, while other super smart beings might be sending us messages that are all lost in translation. We keep waiting for a giant UFO to land on Earth and for green ETs with huge eyes to come out of it. But we forget that our intergalactic neighbors could be more interesting in building nanotechnologies to watch over us. They could also be trying to communicate using neutrinos, which are subatomic particles with an extremely small mass that could effortlessly pass through our planet without being detected by our current technological devices. Now, the zoo hypothesis has another issue. It is pretty tough to believe that, with all these civilizations supposedly hanging out in the universe, they would all decide not to reach out to humans. For this to happen, there would have to be a great sense of structure, with a higher intelligence working as the head of the universe, giving them direct orders and clear rules to keep us isolated. But we're talking about billions of possibilities for life, right? More civilizations mean that there are more chances of a violation of this no-contact rule. So, most likely, at least one independent planet would be just as desperate to find life in the universe as we are. Some scientists also believe that if such advanced life had substantially colonized Earth and many other planets, we would know it by now. The zoo hypothesis has two other variations that are even more frightening. In the laboratory hypothesis, nobody contacts us because humankind is actually being subjected to experiments, and Earth is essentially a giant science lab. Otherworldly creatures could be analyzing human responses to various survival challenges, such as tsunamis or massive earthquakes. In this case, the no-contact agreement between all other space groups would make a bit more sense, since it's in the name of scientific research for the greater good, at least for them. The planetarium hypothesis, proposed in 2001, suggests that we are living in an artificial universe, in some kind of virtual reality designed to give us the illusion that the universe is empty when it's not. But no possible generator could test this hypothesis. Besides the zoo, the laboratory, and the planetarium theories, there is another possible answer to the Fermi paradox. Nobody contacts us because humans are completely alone in the universe. This is known as the rare Earth hypothesis, and it emphasizes how Earth occupies an incredibly unique position. No other planet could bring life to the universe that could be more than just bacteria. We may consider ourselves pretty lucky, as even a small change in any of Earth's orbital parameters, like the distance from the Earth to the Sun or the rate of rotation, could make conditions too extreme for people or life in general. But again, it's hard to think that we are alone in this vast universe. So, we're back to the paradox. Where is everybody?
There are a lot of unanswered questions in physics. How did universal energy and matter appear? Where did gravity come from? And much more. We've been trying for years to get answers to these questions, and one of the people who tried to do this was Paramahamsa Tiwari, the author of the so-called space vortex theory. What is this theory, and what does it say about the hidden laws of our universe? Let's figure it out. Paramahamsa Tiwari was the former executive director of the Nuclear Power Corporation, India. He took the space vortex theory, or SVT for short, first proposed by René Descartes, and finalized it. He was always inspired by physics and its greats, even since his days as an electrical engineering student. After rigorous studies of the laws of physics, he discovered new equations defining matter and the mass and charge of the electron. After that, he came up with the SVT. This theory tried to explain the unexplained phenomena in physics, including the creation of the electron and gravitational, electrostatic, and electromagnetic energy fields, as well as other things. It also described the 6 hidden laws of the universe that underlie our entire world. But first of all, let's talk about the theory itself. Space vortex theory suggests that the universe is made up of vortices, or swirling patterns of energy. And according to SVT, these vortices are the fundamental building blocks of the universe. They're the driving force behind the laws of physics and the fundamental principles of our world. Basically, everything in the universe is connected and interconnected through these vortices. This theory isn't very based on any real observations, but rather on mathematical models and computational modeling. For example, some computational models showed how these vortices work in hydrodynamics and plasma physics. They showed that vortices in such systems can have a central point of attraction and can be interconnected. Other models were used to study how the energies inside the vortices move and how they can create different frequencies and vibrations. But some experts have criticized SVT for using only models and simulations. The biggest criticism is that this theory can't actually be tested. It relies on mathematics and not on some experimental data. That's why it's not accepted as a mainstream scientific theory. But it's still quite interesting and provides a unique perspective on the universe and our understanding of the laws of physics. For example, according to SVT, the universe has some underlying hidden rules that cause the creation of fundamental matter, their assembly, and movement. What are these laws and what do they say? Well, let's take a look at them. Law 1. The universe has only one primordial entity, space, i.e. absolute vacuum, that structures matter. This law states that space is the fundamental building block of the universe and that it's responsible for structuring matter. It suggests that space is the fundamental entity that creates and maintains the structure of matter, and that all matter in the universe is made up of the same fundamental particles, like electrons and positrons. Let's try to put it in simple words. Imagine that the universe is like a big Lego set. Just like how all the Lego bricks are made up of the same basic building blocks, the universe is made up of the same fundamental building blocks too. And these blocks are called electrons and positrons. But what holds these blocks together? Space, of course. Space gives it shape and structure, just like how the plastic container holds all the Lego bricks together in a set. So, the first law states that space is the fundamental building block that structures matter and holds everything together in the universe. Law 2. Matter is constituted with multiples of only one kind of fundamental particles, electrons and positrons. This law states that all matter in the universe is made up of the same fundamental particles, the electron and positron. These two are the Lego blocks we've talked about before. And according to the second law, these tiny invisible particles make up everything from a tiny atom to a giant galaxy. Just like no matter what the shape or size our Lego build is, it's still made up of the same building blocks. Law 3. The field distribution in space, as recognized by contemporary physics, linked with and emanating from matter, are effects arising from only one fundamental field in space. This law states that the fields recognized by contemporary physics, such as the electromagnetic and gravitational fields, are effects arising from a single fundamental field in space. It suggests that this fundamental field is responsible for creating everything that we observe in the universe. So let's try to put it simply. This time, imagine that the universe is like a big playground. All the different fields we observe, such as the gravitational and electromagnetic fields, are like different games we play in there. But no matter what we play, we're still in one fundamental space. This is the playground itself. It's the base that holds everything together. According to the third law, without the playground, we wouldn't be able to play any games. And without this fundamental field in space, we wouldn't be able to observe any fields in the universe. Law 4. There is no void in space anywhere in the whole universe except at the centers of the fundamental particles of matter, electrons and positrons. This law states that there's no truly empty space in the universe and that all space is filled with the fundamental field, the one we talked about before. It says that electrons and positrons can be found everywhere, and even the things we consider to be empty, like vacuum, are actually full of tiny particles. And according to this law, the only truly empty spaces we can find in the universe are at the centers of the fundamental particles, electrons and positrons. Law 5. From only one fundamental universal constant, all the constants considered universal in contemporary physics are derivable. This law states that all the constants considered universal in contemporary physics can be derived from a single fundamental universal constant. It suggests that all the constants in physics are interconnected and can be explained by a single fundamental principle. I know you've been doing a lot of imagining lately, but bear with me. This time, please imagine the universe as a big recipe. All the constants in physics, such as the speed of light, the gravitational constant, and the Planck constant, are like the ingredients. They're very different and there are tons of them. But just like how all the ingredients in a recipe are interconnected and come together to make one dish, all the constants in physics come together to make the universe. And just like how a recipe has a main ingredient that holds everything together, physics also has a single fundamental constant that holds everything together. Law 6. The spatial structure of submicrocosmic fundamental matter is repetitive uniformly in the spatial structures of macrocosmic bodies like planets, stars, and galaxies. This law states that the structure of the fundamental particles that make up matter is repetitive and uniform across all scales, from subatomic particles to macrocosmic bodies like planets, stars, and galaxies. It suggests that the same fundamental principles govern the structure of matter at all scales. Let's go back to the analogy with the recipes and cooking. Using different ingredients and combining them in different ways, the chef can create new dishes. These will all be different dishes and they can be very simple or very complex. But when creating them, the chef still applies the same basic rules and knowledge they have, right? And just like that, the universe also creates different structures, from atoms to planets, stars, and galaxies. But it still uses the same fundamental principles to create all these things. So, this law suggests that the structure of the fundamental particles that make up matter is repetitive and uniform across all scales. These are the 6 fundamental laws of the universe according to the SVT, and even though it's not accepted by mainstream science, it's still a pretty interesting concept. Look at these two pictures. At first glance, one might think, well, aren't they showing the exact same thing? Truth is, they don't. But both these subjects are some of the most complex structures humans have ever had the chance to study. The first image shows a cluster of galaxies from our universe. The second is just a small neuron in the human brain. After seeing these images, some were quick to compare them. Is the universe nothing more than a huge brain? Now let's not get too excited. Before we go into describing all the similarities between the universe and the human brain, there is something we need to be aware of. It's a little thing called apophenia. And it's when our brains make up similarities between two objects that are seriously unrelated. The best example is when we look at clouds and start to see all sorts of cute animals and weirdly shaped objects. We might be doing the same thing when looking at those two initial pictures. Maybe it's just our brain making up similarities where there aren't any. Some scientists became fascinated with this huge brain universe idea. They wanted to make sure it was not just a weird coincidence. There had to be a way they could measure how the universe compares to the mushy organ inside our heads. So they started with the brain. It's probably one of the most complicated things we know in the whole universe. That's because it's packed with more than 80 billion neurons. These cells are responsible for taking information from our senses and sending out messages all over our body. Try to think of neurons as workers in a factory. They don't just do their work, they actually communicate with each other, thanks to these elements called axons and dendrites. The axons are responsible for carrying electrical signals away from the neuron's body to other neurons or muscles. Dendrites, on the other hand, have the task of receiving that information. All of them together make this mega network of about 100 trillion connections. The universe is one big social network itself too, but this time it's made up of galaxies. You might picture the universe as stars and planets with a ton of empty space between them. It's not quite right. What we can see and measure is known as the observable universe, and it's really vast. Think about 90 billion light-years across, containing hundreds of billions to maybe a few trillion of galaxies. These galaxies, like the one we're standing in at this very moment, are bundled together in groups. Our Milky Way is friends, in a way, with galaxies like Andromeda and Triangulum, and altogether, they're a family called the Local Group. This family of galaxies is part of an even bigger bunch called the Virgo Supercluster. From what we can tell, the space between them might not be empty. It's filled with these threads made up of regular matter, but there might also be this mysterious dark matter doing its thing. Scientists didn't stop there. They decided to take it a bit further. They started by examining thin slices of the human cortex, the part responsible for our thoughts, memories, and even our consciousness. The next step was to compare them with equally thin slices of the universe from a computer simulation. Now it's obvious there's this enormous size difference between the brain and the universe. But the way they looked at it kind of made them somewhat comparable. As they zoomed in, think 40 times magnification, these scientists began noticing that the structures were very much alike. At this zoom, the brain's neural network looked like the universe's galaxy clusters. To make sure they weren't just imagining things, they used two clever methods. The first one looked at how these networks connected and how densely packed they were. They noticed that the middle part of a neuron, or its nucleus, is way tinier compared to its connecting fragments. Likewise, galaxy clusters are tiny when you look at the super long connecting threads between them. The second method was about checking how organized these networks were versus just being random. They looked at how everything was structured around each connection point, whether it was a neuron in the brain or a galaxy cluster in the universe. The resemblance doesn't stop there. We know that our brain is mostly water, about 70% to be precise. Now the cosmic web in space, it too has about 70% of something, only this time it's dark energy. Water and dark energy may not be the most important elements in each of their structures, but they might still play a part in how everything sets up. The analogy continues. You see, the space we'd need on a computer to map out the universe is almost the same as our brain's memory storage. Somewhere in the ballpark of 2.5 petabytes. So theoretically, a chunk of the universe could fit in our brains. Or flip that, and our entire life's memories could get stored in the universe's network. There are differences too, and we have to be aware of them to make sure we're assessing things properly. For starters, the universe is pretty much the same all over. It doesn't change its composition that much, regardless of where you travel in the observable area. But our brain, not so much. Different parts have different jobs. Also, our brain connections send information depending on things like what you're seeing or touching. On the flip side, the universe's links are just energy. There's also a difference between how these two structures came to be. It turns out that the patterns we see when we're gazing up at the stars are all shaped by gravity and some weird unseen force called dark matter. Massive fireworks in space called supernovae can also affect this cosmic wallpaper. On the opposite side of the spectrum, our brains got their shape from evolution. That long process where animals, including us, get to pass on the best features and data they've learned to their offspring. So, if a trait like a certain shape of the brain helped our ancestors dodge a hungry tiger, that trait got passed down. Our brains are also built the way they are because they're supposed to act like a superhighway for our thoughts. Quick thinking was crucial for people back in the day when they needed shelter from wild animals or the elements. Now, especially if you're a fan of sci-fi literature, you might be wondering, if the universe is like this immense brain, what might its body look like? We might as well be living in someone else's head. We like to think of humans as evolved, intelligent, and at times, hard to understand creatures. But what if we're just tiny neurons in a larger, more complex structure? Well, for the time being, we can only let our imaginations run wild. There's no way we can test at this point what's outside our universe. By all means, we don't even know how large it is. By looking at the parts we can see, the estimations are that the universe is about 95 billion light-years in diameter. Even if we'd somehow manage to travel at the speed of light, though that seems a bit impossible at the moment too, it would take an enormous amount of time to reach those supposed edges of the universe. There's also the theory of the multiverse. We don't have much tangible proof of this idea either, but it does claim we live in a universe out of many. Ours has time and space. Other worlds may have different rules and components. Life may look differently out there in ways we can't even understand. Having a better understanding of the universe is just as important as figuring out our brains. You see, we still have many unsolved mysteries right here under our noses, or behind our noses to be more precise. There are a lot of things we've yet to figure out about the human brain, like how we store and retrieve memories. We know that each time we learn some new piece of information, our brain changes. But we don't have the entire process mapped out, and it looks like it might take a while before we fully understand it. Imagine the universe as a gigantic, elastic balloon that's steadily being inflated. That's what dark energy seems to be doing, forcing galaxies further apart. Could this force lead to the end of the universe? Some scientists do think so, and they've named this potential event the Big Rip. It's challenging to study dark energy, even though it's one of the most fascinating aspects of our cosmos. That's because its only visible effect is this gentle stretching of space. On any smaller scale, it's virtually undetectable. Compared to dark energy, studying dark matter feels like a walk in the park. Even though it's just as invisible, dark matter leaves clear evidence of its existence. It latches onto galaxies and galaxy clusters, bending light and altering gravity. Dark energy, on the flip side, just expands. Nonetheless, scientists have found ways to examine it, mostly by observing the universe's expansion. As we peer into the distance, we are, in fact, peering back in time, tracing the universe's evolution. Dark energy could also bring about the end of the universe in a massive, catastrophic event. Imagine watching helplessly as reality itself tears apart with no hope of escape. Frighteningly, it's not some far-fetched scenario. The available data does not eliminate the possibility of a big rip. Is dark energy a force that keeps inflating the universe, or is it more like a separator? If two galaxies are far away from each other, they're driven further apart, leading to increasing cosmic isolation. But anything that's already a strong structure stays intact, immune to this divisive force. Why doesn't it mess things up, you ask? Well, it's because dark energy remains consistent. As space grows bigger, the density of dark energy remains steady. Imagine drawing a circle anywhere in space, taking note of the amount of dark energy there. Do it again after 1 billion years, and guess what? The amount of dark energy inside your circle won't change, even though space itself has expanded. That is, unless, of course, dark energy has a trick up its sleeve and proves to be more potent than a cosmological constant. All we know for sure is that it's something that drives the universe to expand more rapidly. Or to put it another way, it creates negative pressure. Now, negative pressure might sound odd. Pressure is usually seen as an outward force, right? But in the universe, it behaves differently. Pressure is a type of energy, like mass, that attracts rather than repels. All these calculations are what makes the Big Rip picture a slow, unraveling movie. The first objects affected are the most massive, loosely bound structures, like giant clusters of galaxies. Their gravitational pull will start weakening, causing them to drift away into the growing cosmic voids. Next, we'd notice stars on the outskirts of our galaxy not following their usual paths, but instead drifting away, like party guests saying their goodbyes. The night sky would then start to dim as our Milky Way would gradually evaporate. The disaster would just accelerate from there. The orbits of the planet would begin to shift, spiraling outward. Just months before the end, after we've lost the outer planets, Earth would drift away from the Sun and the Moon from Earth. We would plunge into the darkness alone. The stillness of solitude won't last, however. Any remaining structure would be destroyed because of the expanding space. The Earth's atmosphere would start to thin. Gravitational shifts would cause chaotic tectonic movements. In the final hours, Earth would fall apart. Beyond this point, the destruction would continue unseen. Nuclei, the ultra-dense cores within atoms, would disintegrate next. Black holes' dense cores would get obliterated. In the last instance, space itself would just rip apart. Bad as it may sound, we may never rule out the threat of a Big Rip. However, it might take so long that all cosmic structures will have decayed before it happens. A rough calculation suggests the earliest Big Rip could be in about 200 billion years. Technically, the Sun still has about 5 billion years before it fades away naturally. So by the time this event might happen, our solar system would have long been gone. Nonetheless, given the possible implications, scientists are placing a high priority on understanding the Big Rip. Let's be optimistic though. I mean, if we look at the universe's history, we should consider ourselves lucky. We're in what cosmologists refer to as the luminiferous era. It means that right now the universe is still pretty busy producing new stars, and we know how important these celestial bodies are for maintaining life as we know it. However, the golden age of star formation was about 10 billion years ago. Ever since that peak, the rate of creating new stars has been on the decline. Now, why is the universe taking this early retirement? It's not because it's lazy or tired. In fact, it's exactly because we're living in this expanding universe. For a new star to appear, a bunch of matter needs to be squeezed into a relatively small space. It's like trying to stuff all your clothes into a very, very small suitcase. As the universe expands, the matter is getting spread out, leading to less and less room in that suitcase for creating new stars. The Big Freeze, another theory related to the end of the universe, looks at this scenario. Stars will become endangered and then extinct species. This period of star decline is what astronomers like to call the degenerate era. It's estimated to start about 100 trillion years into the future. What'll be left in the night sky at that point? Only the hardened workers of the universe, white dwarfs, neutron stars, and black holes. White dwarfs and neutron stars, the remnants of medium and large stars that have exhausted their nuclear fuel, will eventually cool off and transform into black dwarfs. These black dwarfs are like invisible cosmic spirits, just hanging around without doing much, inert and unseen. Other neutron stars, too heavy for their own good, will stumble under their weight and collapse into black holes. Further into the future, the universe will become a black holes only party. But even these cosmic weirdos can't cheat time forever. Black holes can fade away too. In fact, this idea of fading black holes came from a brilliant mind you might have heard of, Stephen Hawking. He suggested that black holes slowly shed energy in the form of radiation until they shrivel up like raisins and evaporate completely. Eventually, every single black hole will have evaporated. We'll be left with a universe in its twilight years, settling into its final age. aptly named the Dark Era. At this point, both light and matter will be nothing but distant memories. And then, well, nothing. If this big freeze theory is correct, the universe will just remain in a quiet, dark state stretching into an eternity where nothing else ever happens. Most of these theories seem to rely on the fact that the universe is expanding. But what exactly is it expanding into? We can't help but wonder if there's something else beyond our universe. Right now, this question is one for which physics doesn't quite have an answer for. We don't have enough facts. One suggestion is that time and space came to be with the Big Bang. That happened around 14 billion years ago, so logically there's nothing beyond the universe. However, a huge chunk of the universe is way out of our sight, existing beyond the part we can observe, which is about 90 billion light-years in diameter. Because everything's pretty much the same wherever you look in the universe, we can presume that the bits we can't see would look pretty much like the parts we can. But that's just an assumption. Now, if the universe is infinite, there's nothing beyond it, right? I mean, that's just what infinite means. On the other hand, if it's finite and growing, you'd start to wonder if there's a boundary or an edge, like a universal cliff that separates our universe from whatever is beyond it. It gets even more complicated when you realize the universe has at least 4 dimensions, 3 for space and 1 for time. And it's pretty much impossible for us to picture what that might look like.
Now, when we say the word universe, we're already picturing this vast space filled with stars, planets, and comets. Truth is, most of us find it hard to actually picture how large the universe is. Well, try to think of space as the biggest playground you've ever seen. Right now, our space playground goes on for 46 billion light-years. It wasn't always like that. On that note, you've surely heard of the Big Bang Theory. Let's try to unpack it. Imagine the whole wide universe, every star, planet, down to the smallest particle, squished into a tiny super-hot ball the size of, let's say, an apple. From that point on, we've got a pretty neat roadmap of how things unfolded in the cosmos. Dive even deeper into the universe's past, and things start to get a bit blurry. The energies and temperatures rise, and suddenly, our rulebook of physics doesn't make sense anymore. When we reach these early times, gravity, that force that keeps our feet on the ground, starts acting all mysterious. This is where we bump into the great puzzle of our time, quantum gravity. And here's the honest truth, we've still got some homework to do on that one. What made the Big Bang go pop in the first place? Well, it's kind of like asking what happened before the first page of a book. There's no page 0, or at least that's the answer that quantum physics provides. It tells us that there are events in the universe that just, happen. It's not because we're not looking where we should, it's just how the universe works. Or at least, that's our current understanding of it. Right after the blast, everything was just a bubbly mix of gas, like this soda can that just got opened. This gas, which was mainly helium and hydrogen, began to stretch out and cool down. If we could time travel to those times, we'd see a younger, hotter, and cozier universe. Cool telescopes like the Hubble and James Webb let us peek into those ancient times. And what we see is fascinating. Earlier galaxies were like the cute photos of the universe when it was younger. Tinier, less heavy, and not as evolved as they are now. Over billions of years, the universe stretched out like a soap bubble. Imagine countless shiny marbles inside it, representing stars and galaxies. As the bubble grew bigger, the marbles spread out. Today, inside our bubble, we have trillions of galaxies. For every single galaxy we can spot, there are tons more we haven't seen yet. Some are too tiny, others are too far away. We still can't see them even if we use the fanciest telescopes available. Just to paint you a better picture, know that today, our very own Milky Way is home to around 400 billion stars, similar to the Sun. It was a lot different in the past, though. Our galaxy began its journey like a little bundle of stuff, just a tad denser than most things in space. A lot of it was actually made of dark matter. Our closest star friend, named Proxima Centauri, is 4.2 light-years away. To put that in earthly terms, That's like taking a road trip around our planet millions of times. It's also about the same age as the Sun. If we could have looked at the exact spot about 5 billion years ago, it wouldn't have been there at all. Many stars live together in groups, kind of like families. However, most are solo adventurers, experiencing the vastness on their own. When you zoom out from our Milky Way and peek into the larger universe, it's more, well, empty, like a vast piece of countryside between big cities. In our cosmic area, we've got some cool neighbors. The Andromeda Galaxy, for instance, is just a stroll away, in cosmic terms, at 2.5 million light-years. And there are lots of smaller galaxies too, like the Triangulum Galaxy and the Large Magellanic Cloud. Our local hangout spot, which includes all these galaxies, spans about 3 million light-years. As we explore further, galaxies seem to gather in clusters, like suburbs. Connecting these clusters are threads of galaxies, creating a giant web in the universe. Galaxies are clustered this way because, just like magnets, they love to pull stuff towards them. If we could turn back time, we'd see a different picture. That's because throughout history, the popular galaxies with lots of stuff became even bigger, while the less popular ones gave their items away. From Earth, we can only see objects that are 46 billion light-years away at the most. If we put all this space into a giant box, its volume would be unimaginably huge. The main reason our universe is such a grand spectacle today is that it's been growing nonstop. Every year, its size increases a little more. In fact, the universe is expanding faster than the speed of light. Sure, we can't feel it down here on Earth, but there are clear signs in the universe that it's happening. We're still not sure why the universe behaves like that, but scientists are working hard to figure out this mysterious expansion. Our understanding of the universe has changed a lot over the years, too. Back in the day, when our world had more trees than buildings, people from all corners of the Earth would gaze up at a twinkling sky above. For many, the sky was their roadmap, alarm clock, and spiritual connection point. Now, imagine not having a smartphone or a compass, and still being able to find your way home or knowing when to plant your crops. That's because our ancestors had the sky. They knew when it was time to take care of plants, navigate ships, or celebrate special occasions, all by watching the stars and planets. Long ago, people in Babylon spotted some stars that behaved a little weirdly. These stars seemed to have a mind of their own. Obviously, we know now that they weren't stars at all. They were planets, like Venus and Mars, that sometimes wink at us down here. There was also a time when we believed the Earth was flat. Well, at least some people did, before Greeks in the 6th century BCE figured out that it's round. They even managed to guess its size by watching shadows in different places. They were pretty close with their estimations, especially if you take into consideration their limited tools. Now, speaking of our planet, there was also a time when humankind believed the Earth to be the center of the universe. We also believed everything else was just spinning around it. That was until a man named Copernicus did a bit of research and figured out it was actually the sun coordinating all the movement in our system. And soon after, other thinkers and stargazers joined in on the fun, changing how we perceive the universe using new tools. Speaking of tools, thanks to a telescope, Galileo found out that Jupiter had massive moons tagging along. We call them the Galilean moons today in his honor. But the universe kept tossing surprises our way. Some people started cataloging stars, clusters, and nebula, while others found mysterious rays that our eyes can't see. And just when we thought we had it all figured out, Edwin Hubble, not the telescope but the man behind the name, discovered something amazing too. He realized that other galaxies are in fact moving further away from us. These days, we're looking at the universe in a different way. We know how the timeline works now. We know that our time here on Earth is limited. No wonder astronomers are eagerly scouting through the vastness of space, looking for planets similar to ours. There is no other planet that can safely accommodate us in our solar system. But we can use our neighboring planets and satellites for scientific purposes. Take Mars, for instance. In the following decades, NASA is planning to send all sorts of devices and even people up there. If the experiment proves to be successful, we might end up living there for a while, or at least use it as a pit stop for our next exciting destination.
There's this mysterious thing in space, an unusual spot that scientists haven't been able to explain for more than 15 years. There are different theories, and one of them says that maybe this is an imprint from a collision with a parallel universe. Is this true? Well, let's see. Take a look at this map. This is the map of our universe. Well, not really. This is actually the map of cosmic microwave background radiation, or simply CMB. Many billions of years ago, there was a Big Bang. It was so powerful that it created our entire universe. And, of course, such an event couldn't occur without leaving some consequences. And these consequences are literally everywhere. The Big Bang left electromagnetic radiation, which we know as CMB. We don't notice it in our daily lives, but it's literally here, under our noses. And if you had some kind of superhuman vision, you would see how everything around you shines with this dim light. This radiation is very important. If we hadn't discovered the CMB, we would never have found out about the Big Bang. Previously, scientists believed that the universe had always existed. There was no beginning and there was no end. It sounded pretty ridiculous to us now, but less than a century ago, people were absolutely sure of it. Stephen Hawking was one of the first scientists to guess that the universe did, in fact, have a beginning. The guy was so cool that he realized this as a student while working on his doctoral dissertation. But unfortunately, he had no proof. If there was such a strong bang billions of years ago, then where are the traces? Where's the proof? Laughed people who believed in the eternal static universe theory. But don't worry, they had the proof rubbed in their faces real soon. In 1965, astronomers Arno Pienzas and Robert Wilson discovered CMB, and that was the first grandiose proof of the Big Bang. It turned out that radiation was everywhere. We just didn't notice it. In fact, at first, Pienzas and Wilson themselves mistook it for the noise of a big city, or pigeons, or something else. For their discovery, which turned the world of science upside down, they received the Nobel Prize. Alright, so people learned that they were surrounded by electromagnetic radiation. Then they started collecting more data about it. They accumulated more and more info over the years until they made this very map. This is a map of CMB temperatures. But while creating it, scientists discovered something unusual. Let's take a look at this map. It looks like a large and diverse pattern of cold and warm places. But in reality, our universe is quite uniform. All temperatures on this map are close to negative 455 degrees Fahrenheit with very little difference. All temperature fluctuations between these places are small, and each tiny speck actually spreads over millions of light years. So everything in our world is pretty calm and stable, except for one point. This cold spot right here. Astronomers first discovered it in 2004. First, it looked like nothing unusual. It's just a region where the temperature is below average for a couple of microkelvins. But remember, we're not talking about a small area. This is a giant cold region. It's literally billions of light years in size. Wait, the scientists thought, this can't be true. The universe should be consistent everywhere. According to our standard model, this cold spot simply shouldn't exist. But it does exist though. This isn't just some mathematical error, it's right there. So what is this cold spot, and how did it appear? Astronomers have been trying to find the answers to these questions for years. Even now, we have only a few theories. So let's discuss them all. Theory 1. Cosmic texture. This idea was brought up at the end of 2007. Then scientists suggested that this cold spot could be the hills of space. In other words, it may be a bumpy region of the universe, just part of its texture. But that's a silly explanation, so this theory was quickly discarded. Theory 2. The supervoid. This hypothesis was considered the most plausible for a while. It stated that the cold spot was actually the so-called supervoid. It's a terrifying, dark place of our universe with almost no galaxies. And because it's an empty region with almost no stuff in there, it seems cold to us. However, this theory was refuted in May 2017. After carefully examining the cold spot, scientists found out that there were no signs of a supervoid there. Moreover, voids and supervoids, which actually exist by the way, are still very small in size. The cold spot is literally thousands of times bigger than them, so there must be some other explanation. And there is one, perhaps the most bizarre of them all. Theory 3. A parallel universe. This controversial idea was put forward by cosmologist and theoretical physicist Laura Mersini-Houghton. She suggested that the cold spot could be an imprint from the collision of our universe with a parallel one. Standard cosmology cannot explain such a giant cosmic hole, says Mersini-Houghton. This is the unmistakable imprint of another universe beyond the edge of our own. Her assumption is based on the theory of the multiverse. This theory says that there's actually an infinite number of universes like ours in the world. They constantly collide with each other, giving each other a push which creates a new Big Bang. So maybe the cold spot is a bruise from such a collision. For quantum mechanics, such crazy theories are pretty common, but for standard physics and our simple understanding of the world, this is earth-shattering. Of course, we need strong evidence. And Mersini-Houghton's team has begun to work on it. Professor Tom Shanks from the Center for Extragalactic Astronomy at Durham University also participates in this research. The craziest sounding of the exotic models for the explanation of the cold spot, the multiverse is actually the most standard in terms of our current model of the universe, he wrote in one of his works. So, what evidence do we need? Well, our cold spot is located in the southern hemisphere. According to Shanks, if there really was a collision between two universes, we should find another cold spot, and it should be in the opposite northern hemisphere. If astronomers actually found it, this theory would be confirmed, and it'd become the first proof of the existence of a parallel universe. But it's not that easy. To find a second spot, we need the latest, highly sensitive telescopes. We also need to find out some info about the nature of dark energy, how it affects space, and, in other words, there's still a lot of work to do. Not so long ago, scientists actually believed they had discovered the second spot. Researchers from New Mexico thought they had found it in the northern hemisphere. But unfortunately, this is likely to be a mistake. The map these researchers used had a high measure of randomness, so it's possible that their discovery is just an accident caused by other voids. So, basically, we haven't found another cold spot so far despite careful analysis. But again, even the best modern equipment is not perfect, and it doesn't mean that there's no second spot. It just means that we haven't found it yet. But if one day we did find it, it could change the world of science forever. We'd confirm not only the theory of parallel universes, but also the famous string theory. It could explain everything that occurs in our world. But if this happens, we'll get even more questions than we already have. How did these two universes collide? How does it all work? So far, it's all just guesswork. We can't claim that the cold spot is a print from the collision of parallel universes. But we can't refute this either. Actually, we may never know the truth at all. But it's still interesting to strive for it.
13.8 billion years ago, a mysterious explosion happened in space. It was chaos, a time when the stars, planets, asteroids, the rest of the space bodies, and galaxies were born. It was the Big Bang, a theory we all know about. But no one knows for sure what happened, where the universe came from, and what was there before. Some even think the universe went through a cycle where it contracted and expanded several times. In 1991, A cosmologist from Stanford University named Andre Linde had submitted an article with the main idea that there was a possibility the universe had been created in a laboratory. His theory said there was a chance an advanced civilization somewhere out there had created our universe. This civilization has made an entirely new cosmos that later evolved its own planets, stars, and intelligent forms of life. 30 years later, many scientists take this theory pretty seriously. They even started talking about things that we, as a civilization, can do to get to such an advanced level. The theory says this advanced civilization decided to add technology that helped to create a new universe out of nothing. It happened through quantum tunneling. It's when an atom can appear on the opposite side of some barrier, even though it's supposed to be impossible, considering the laws of physics of our world. Like if you wanted to pass a tall wall, but you can't pass it with ladders or go around somewhere. Imagine you can just walk through it like a ghost. In our world, it's not possible, but a more advanced civilization perhaps can do it. Plus, they realized how they could create new universes. Right now, on the cosmic scale, we could be a Class C civilization. We don't know how to recreate some things. For example, conditions on the Earth for when our central star, the Sun, goes out. If we manage to become a Class B civilization, we'll learn to adjust conditions to be independent of the Sun. That means we might be able to learn how to live even without it. And if we level up and become Class A, we'll know how to recreate cosmic conditions and produce our own cosmos in our laboratories. We think of the world we live in through 3 dimensions of space: east, west, north, south, and up, down. There's also 1 dimension of time, which means we can distinguish past from future. A 5th dimension would represent 1 more extra dimension of space. The theory of its existence was first mentioned in the 1920s. It was inspired by the theory of gravity by Albert Einstein, who said space-time is warped by matter and energy. We can't perceive these 4 dimensions, but we see how an object moves and attribute it to gravity. And maybe there's some other force, like the electromagnetic force, that's more than 1,000 times stronger than gravity, that could explain things going on in that extra dimension of space. The 5th dimension is curved in a way we can't see it, but the idea about it was mentioned in a string theory. It considers the universe as really small strings of mass energy, not as particles. They vibrate in 10-dimensional space-time, considering 6 dimensions are rolled up way smaller than a single atom. That led to the picture of the universe as a 3D island that floats in 10-dimensional space-time. Also, the 5th dimension might be an excellent explanation to tell us more about dark matter. That's the invisible stuff with a mass, but we can't see it, nor can it interact with ordinary matter. And dark matter is 85% of all the matter in our universe. The universe can't be still. It's constantly in motion, either contracting or expanding. We used to think there were 100 billion galaxies, but it turns out there are more than 1 trillion. The galaxies are moving away from each other. This is what it means when scientists say the universe is expanding all the time. There are voids between galaxies that sometimes stretch millions and millions of light years across. They can seem empty, but they can also contain way more matter than we can find in galaxies. Still, stars usually can't be formed there because the matter between those areas has lower density. But there's still plenty of so-called intergalactic stars. A good example is the Virgo galaxy cluster, 10% of which are intergalactic stars. We don't know how exactly they got there, but there are 2 possible ways. 1. Stars can collide, merge, or pass close to another galaxy, which can kick it off from its parent galaxy. Option number 2. A supermassive black hole can accelerate a star to very high velocities if they have a close encounter, which can, again, make a star be expelled from its parent galaxy. If you could have a giant magnet, you could even pull something out from the vicinity of a black hole. That's possible if the magnetic field near a supermassive black hole is as strong as the black hole's gravitational field. But it doesn't work if we're talking about material that's already beyond the black hole's event horizon. That's a spot with a gravitational force so powerful, not even light can get away. You'd need to accelerate this material to the speed of light, at least, to get away. For that, you'd need an infinite amount of energy. But a magnet could help if something's heading toward the black hole but didn't get inside yet. When someone mentions a black hole, you might get a picture of some giant void in space. But the Milky Way is most likely full of thousands of smaller black holes that float around the galaxy. When a star comes to its end, it will destroy itself in a supernova explosion, which is a cataclysm of energy. In that explosion, the densities in the core will reach an intense enough state that nothing will be able to escape. At the same time, the major part of the star explodes outward, but a part of it collapses inward, creating a black hole. The bigger the star, the bigger the hole. The black hole then swallows everything that comes in its way, including other stars as well. When a star gets sucked up into the black hole, it's ripped apart because of the strong gravity inside the black hole. Some of its parts fall into the black hole, while others get ejected at incredibly high speeds. Some black holes might have been formed in a different way. The early stages of our universe were, to say the least, pretty chaotic. It had high temperatures and pressures, and was in a state that shaped the entire cosmos. Under the right conditions, any old gas patch may have shrunk itself to become a black hole. And they came in many different sizes, from something that weighs a couple of pounds to giant masses like thousands of suns, and those in between. They aren't really black. Black holes are areas with strong gravity, and no object can escape when it gets inside. They feed off electromagnetic radiation, such as light and space particles. Since they're consuming matter all the time, black holes give off a dark glow. The Earth is not that close to the inhospitable edge of the solar system. We're the sixth planet from it. Scientists made a pretty cool 3D map of our solar system, where we can see what the edge looks like. It took them 13 years to design it. The boundary is called the outer heliosphere. It marks the area in space where the solar wind, which is the stream of charged particles our sun emits, gets deflected and draped back by the radiation coming from the empty region beyond our solar system. The inner layer of the heliosphere is where the sun and the planets have a rough shape of a sphere, while the outer layer is not that symmetrical. This asymmetry happens because our sun is moving through the galaxy and goes through friction with the radiation in front of it. Black holes tearing apart enormous stars, pulsars spinning at incredible speeds and emitting powerful beams of energy, colorful nebulae with fireworks of newborn stars, galaxies of every possible color and size. All of these are found within our universe, but it's not infinite. It has a boundary, a literal wall, and beyond that, there's an absolute nothingness. Right now, we're going to make a journey to that wall. But first things first, our universe is like a humongous nesting doll. If you open it up, there's a smaller one inside. It's a galaxy. Inside that is an even smaller doll. That's our solar system. And the smallest doll of all is the Earth. Each of these dolls has boundaries that we're going to cross. For that, we'll need a spaceship, and a big one. It also has to be able to move 100 times faster than the speed of light. You get on board and start the engines. 62 miles above sea level is our first boundary. That's 10 times higher than passenger planes fly. This point is called the Kármán line. It separates the atmosphere of the Earth from outer space. Now we fly further to the edge of our solar system. We turn on the hyperdrives and fly past Mars, Jupiter, Saturn, Uranus, and Neptune. We've traveled a distance of 100 astronomical units. 1 AU is the distance from Earth to the Sun. And here's the boundary of our solar system, the heliosphere. Here, the speed of the solar wind decreases rapidly. First, it drops from 620,000 miles per hour to the speed of sound. Then, there's a layer called the heliopause. This is where the wind almost vanishes. And then, our ship experiences a bow wave. This is where we feel the force of the interstellar wind, which collides with the boundary of our solar system. When you pass this boundary, you find yourself in the dark of interstellar space. And here, you can find two human-made objects that made this trip for the first time in history. They're Voyager 1 and Voyager 2. Voyager 1 crossed that boundary in 2004. Voyager 2 did it in 2007. These space probes discovered that the heliosphere is not a perfect ball around the sun. Its southern boundary is 10 AUs closer to the star than the northern one. So, We're moving in interstellar space and will soon approach a stone wall around our solar system. 200,000 AUs further, and there it is. This wall of rock is the Oort cloud. In fact, it's a pile of asteroids that surround our world. Scientists speculate that the Oort cloud could be the source of comets and meteorites that fall to Earth, but they're so sparse that we easily fly between them. Now we're in complete darkness. The Milky Way is about 106,000 light-years wide. In a conventional rocket, it would take billions of years to fly across that distance. But you throttle to the max. You masterfully fly past the stars and planets as if on a racetrack. And within minutes, you're at the edge of our galaxy. There's no more interstellar wind. All you see are bright dots somewhere in the distance. These dots are huge galaxies. We need to look at a map to make a route to the edge of our entire universe. You're here, near the Milky Way galaxy. It's part of a cluster of galaxies called the Laniakea supercluster. But even this huge thing is like a little street in a big city. Zooming out, we find Hydra Centaurus supercluster. Thousands of galaxies on the map look like little dots. Maximum zoom out. This is our entire observable universe. We thought it was infinite, but we may have proof that it has a boundary. It's here, 10 billion light-years away from our home. Even if you travel at the speed of light, a trip there would take twice as long as our whole planet has existed. During that time, the sun will either fade away or explode like a supernova, destroying our entire solar system. And if you can live that long and then return home, you will see that our galaxy is there no more. It's long since collided with the Andromeda galaxy and merged into one big cosmic body. Luckily, your ship is able to warp space-time so that this journey will literally take a few seconds. Boom! Congratulations! You've arrived at your destination, the Eridanus supervoid. Some scientists believe this location is the evidence of collisions of our universe with something big enough to leave such a large scar. The Eridanus supervoid is an empty and cold space 1 billion light-years wide. If you think of this void as a cup, it would fit at least 10,000 galaxies, and it appeared after an accident of gigantic proportions. The object that crashed into our universe was another universe. Yes, other universes may actually exist. Imagine that our entire universe is a huge bubble that contains all the clusters of galaxies in the observable universe. There could be an infinite number of such bubbles. They could have been born during the Big Bang. These universes may be different from ours. They may have other galaxies and nebulae. But these bubbles could also be parallel universes. This means that if you chose cereal over oatmeal in the morning, in another universe, your twin would choose the oatmeal. Every choice you ever made in life had completely different consequences in a parallel universe. And because the number of choices are infinite, there's a whole infinity of parallel universes. So, like a regular bubble, our universe has a wall that is near the Eridanus supervoid. Long ago, another bubble flew past ours. As they approached each other, their gravitational fields began to interact. Our boundary wall began to deform and pull toward the other universe. The same thing happened on the other side. Then the walls of our universes came into contact. But as these bubbles moved, their connection began to break, and the other universe just ripped a huge chunk of ours. A cold void was formed at the point of collision, and that was the Eridanus supervoid. The problem is that the universe looks the same to the observer, regardless of point of view. For example, imagine a basketball hanging in the air. Now, if we put an ant on the ball and tell it to find the edge of the ball, it will start running around it, making an infinite number of circles. But the landscape around the ant will not change. All it will see is a rounded horizon. That's because the ball remains the same from any point of view. The same thing happens to us when we try to find the edge of our universe, all because we imagine the world in three-dimensional space, and our view is limited. For example, you see an ordinary square in two-dimensional space, but if you add depth and change the point of view, voila, it's a cube. If we could see the universe in four-dimensional space, a square might be something completely different. But maybe we can leave our home bubble. The key to traveling to another universe might be inside a black hole. A black hole is one of the most mysterious objects in the universe. They're so heavy, they warp not only space, but time as well. It's like putting a heavy boulder on a net. The net will sag, and the closer you get to the boulder, the stronger the curvature is. Once you're in the gravitational field of a black hole, you can't leave it. We still don't know what might actually be in the heart of a black hole. Some scientists speculate that white holes also exist. Theoretically, they should be born along with black holes. Except for the color, they're the exact opposite of black holes. Nothing can come close to a white hole. At the moment, there's no data on such objects, but general relativity theory suggests they do exist. There's also a theory that a black hole may be a passage to another universe. When you get into a black hole, you can come out the other side through the event horizon of the white hole. So you bypass the boundary of the universes and find yourself in a completely different world. But we may have proof that a white hole exists. In 2006, scientists discovered an unusual burst of energy somewhere 1.6 billion light-years away from Earth. This burst was unique. It didn't look like a supernova explosion or even the merger of two black holes. Some astronomers believe it was the birth of a white hole. But because it was unstable, it was destroyed almost immediately. This process was reminiscent of the birth of our entire universe, the Big Bang. So, scientists called it